Good day all, and welcome to this chemistry masterclass on this nice, bright and early Saturday. So as you can see, it's chemistry. But before we begin with this lesson, we have to go through some ground rules, and I'm pretty sure most of you know the ground rules by now. But as you can see, your chat as well as your mics is not enabled. That is because we do not want any distractions while we are busy presenting, or while other people are maybe busy making notes while they're trying out these different lessons. Another thing that I would like to say for everyone is that please engage in this lesson. If you have any questions, you're more than welcome to type it in the chat. And while we're speaking about the chat, please write down your name and your school name, as well as how many people are watching from your device. That is mainly for our record keeping purposes. So before we begin with this actual lesson, I also want to say I hope that everyone wrote physics paper 1 quite nicely and that our Wednesday lesson really helped out with that as well. Now, chemistry is set up very similar to physics. We start with multiple choice questions. So let's move on to our first multiple choice question. So here it states 1.1. Consider the flow diagram below. And it's given over here. Here it is told to us that is propene. And then we added a hydrogen molecule with platinum as a catalyst. And that will give us compound X. Then it says compound X could either be A, propane, which is a YNE, so in a triple bond, B, propane 1-ol, C, propane, or D, propane 2-ol. So if that is the case, this molecule is going to look like this. So we'll start with our propene. So it's meth, eth, prop. Propene means it's a double bond. It's not specified what the double bond is, but because there are only 3 carbons, we know it can only be either on the left-hand side or the right-hand side. So that is our 2 carbons over here. Right, sorry, a double bond over here. And then that has carbon can always only have 4 bonds. So that means there'll be a hydrogen over here. So that's first carbon has all of its bonds. Then there's 1, 2, 3. So this will mean it will only have 1 bond. Then it's 1, 2, 3, and 4 bonds. So there's our propene, and then we add our H2 to it. So that means we're adding 2 hydrogen molecules. And that is now going to break up the double bond, and then 1 hydrogen will be over here, another hydrogen will be over here. So if we write that out, it will look like this, a H here and a H here. So we are going to take the eraser, erase this away, and therefore we can see that if you add hydrogens to it, this is what it will look. And what is this called? That is just propane with a single bonds everywhere. So therefore, our answer is going to be C, propane. Remember, multiple choice is just worth a 1 mark, and that's how we sort this one out. Another hint was given was the platinum. Whenever we have platinum, palladium, or nickel, then that is going to be when you are going to go from an alkene to an alkane. Next, 1.2 states, which of the following compounds has the highest vapor pressure? Is it going to be ethane, propane, butane, or pentane? So all of it here, we can see that it ends in ane, which means it's all single bonds, right? It's not an alcohol, carboxylic acid, nothing like that. The only difference is how many carbons are in there. So this is F, so that means there are 2 carbons within here. Prop means there are 3 carbons, but means there are 4 carbons, and pent means there are 5 carbons. So in this particular case, when it comes to vapor pressure, remember vapor pressure. So if you increase in your vapor pressure, I'll just write it as Vp, then that will automatically mean the molecule will have a very low boiling point, because these are inversely proportional to each other. So therefore, if you have a very low vapor pressure, then that means, so I'll just put the equal to between it, that means you'll have a very high boiling point. So in this particular case, the higher or the more carbons you have in your chain, that would then mean you have a higher boiling point. So in this case, the more carbons we have, which is pentane, will have a very high boiling point, but then that means we'll have a very low vapor pressure. So instead, what we need to do is we need to see which one has the lowest carbons, because that will then mean it will have the lowest boiling point. Therefore, it will give us the higher vapor pressure. So this answer is going to be A, ethane. Right, and you guys are more than welcome to type your answers in the chat as well. Moving on, 1.3. During the dehydration of butane 2-ol, represented below, which is this over here, a major organic compound Y is formed. Then it asks from us, which of the following is the correct condensed structural formula for compound Y? Is it going to be this or this? Now, I know for multiple choice, there is usually 4. I have the other 2 on the other slide. But when we have the condensed structural formula, the first thing you always do is you try and write it out in a structural formula to make sure you know what is happening. So the first thing I'm going to do is, before I write down the structural formula of my options, let's write down the structural formula of the question given to us. So we're going to begin with this first one over here. So CH3. So I'll put the H here, H here, and then H here. We are starting with this part. So that was CH3. Now I move on to CH2. So that will be our C with our 2 H's over here. Then we have our C with an H, which is this part over here. And attached to that is an OH. So here we have an O and an H. Then afterwards, we have this part here, which is CH3. C with an H3. H, H, and H. This is our first molecule. Now it is saying it is a dehydration reaction. Remember, whenever you hear dehydration, that means you don't have that much water. So what we are basically doing in this chemical equation, we will be taking a water molecule away from that. So if we're going to take a water molecule away, we all know it is H2O. So that means we are going to take this OH away from the one carbon. Now, in order to get water, you need another H. Please do not take this H as well. Do not take everything from the same carbon. You're going to take from the carbon adjacent to that one, which means it's next to that one. So, bring out my pen again. So it can be on the right-hand side or the left-hand side. So let's see, for instance, let's say, for instance, I'm going to take this one over here. So I'll take those. Then that means that's going to be written as, now I'll write it on the right-hand side. I'll have it like we had at the start with our C and our 2 H's. This is just me following along with what we had, our C with our H. Then we have this C, that H, that H. I took the water molecule away, so this will, of course, be added to HOH. That is product. And now that there are, both of these only have 3, so we'll make it the double bond over there to suffice the amount of bonds for carbon. So this is actually molecule Y. So what we now need to do is, we now need to see which of our options, A, B, C, or D, is that molecule that we have. So now we're going to erase this out of the way, because we know water is a byproduct, but that's not the main important part that we are focusing on. So dealing with A, we'll start off over here. So that's our CH3, 1, 2, and 3. Then we move on to our CH2, which will be our CH2 here. Then we move on to our other CH2, which is this one, CH2. And then we move on to CH3, 1, 2, and 3. So clearly that is not compound Y, so we know A to B. We will change up the ink. Let's maybe make it blue. Now, CH3 again. So 1, 2, and 3. And then we move on to our CH. So only one H over there, that is a spot. Then here, it's also a CH. And then we move on to our CH3. 1, 2, and 3. So as you can see, this carbon only has 1, 2, 3 bonds, and this carbon also only have 1, 2, 3 bonds, which means we put the double bond in between those over here. So there we can see we have an alkene, but it's not similar to the one that we have on this side. But before you rule that out, if you look at the side I had over here, we were allowed to take a hydrogen either from this side or that side, which means if we had to do that, our compound would have looked like B. So that means B could be an option depending on where you took a hydrogen away from. But now we move on to C and D. So let me get my marker again. Go on. Okay, there we go. Just changing the color. Let's move on to like a maroon, CH3. So we'll go again about that. 1, 2, and 3. And then we have our CH2, which is this. Then we move on to this, which is CH, and that is attached to an OH. OH. And then that is attached to a CH3. We could then say, so not this as well, because remember we took the wood, we had to take a water molecule away. This is an alcohol, so we took that entire part away. So this is also out. So we move on to our last one. So this CH3 over here. Then we had a CH2. And then we had a CH. And this is a CH2. This carbon has 3 bonds. This carbon has 3 bonds. So you put a double bond in between the two of those. And that is what I had for my reaction over here. So we're going to say the answer is D. But you were allowed to actually say it's B or D in this particular case. They actually would have marked you right. So if you wrote B or D in here, you will get the answer. It all depended on where you took your hydrogen away. Moving on, 1.4. The complete combustion of 1 mole of butane needs at least, in here they give the options, A, B, C, or D. Either 18 moles of oxygen, 5 moles of oxygen, 7 moles of oxygen, or 13 moles of oxygen. So, in order for us to do this, we can see if it is A, B, C, or D. It was a bit of a tricky one. But now to make sure that you guys also know what's happening, can everyone please try and answer in the chat with A, B, C, or D by answering question 1.4. Okay, I'm just trying to get to the chat quickly, so everyone, so I can see what you're typing. Okay. This on. There we go. Okay, so okay, there's a few answers for A, few answers for D. What? Yes, there's a C, there's D, quite a lot of D's as well. Okay. Okay, so there's quite a lot of those answers. Okay, so let me show you what I have for this. So I'll just make this a bit bigger now so I can see better. Okay, so now in order to answer this, whenever they speak of a combustion reaction, remember combustion reaction is always an alkane that is added to an oxygen, which is O2, the oxygen molecule, and that will always give you a water molecule, which is H2O, and that is added to carbon dioxide, which is CO2, right? So that is the general formula for a combustion reaction. So in this case, they told us it's butane. So we know butane, that means there are 4 carbons, meth, eth, prop, bute. So just to make sure that everyone follows along and see what we're doing, 1, 2, 3, and 4, then there are different hydrogens. So that will be 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 different hydrogens. Now, I'm not going to now write all the other hydrogens out. I just shown you that's where the hydrogens will be. So that means for butane, it will be C4H10. You could also just go with the general formula. We know a CN, H2N plus 2, because it is an alkane. So we know that is now our initial formula that we need, right? So we're going to go about it this way. Let's go back to our pen. Now we need to see how much we're going to need of this carbon. So the first thing we're going to do is we need to balance this above formula. And we're going to do it in terms of CHO, which is CHO. So I'm going to change the parts for all of this. So we're first going to balance our carbons. So the C's. Now, on the left-hand side, we see that there are 4 carbons. On the right-hand side of our arrow, there's only 1 carbon, which means if you put a 4 in front of that, we'll now balance that out. So that is now going to be 4 on either side. Now, we move on. Remember, I said we're balancing in terms of CHO. So that means it's going to be, let's make it blue, CHO. So H. Now we look at our hydrogens on the left-hand side. We have 10 hydrogens. On the right-hand side, we only have 2 hydrogens. So that means we will put a 5 in front of this, because 5 multiplied by 2 is 10. Then, of course, the last one is going to be, let's check another color, oxygen. Oxygen's on our left-hand side. Remember, there's a 2, subscript 2 by the oxygen, so that means there are 2, which means on the right-hand side, we're going to now count this. So that's going to be 5 multiplied by 1 is 5, and then 4 multiplied by 2, right, is 8, right? So we know that 8 plus 5 is equal to 13. So what you can do is you can write a 13 over here over 2. And that will actually make your equation the same on both sides. Now, the reason why I say that is because if I don't want anyone to get confused, because now these 2 will cancel out with each other. Let's divide that, will cancel with that. So it will be 13 of this. But okay, now let's move back. And let's write down what we have. So color was 2, so I'll still write it as, sorry, bring a pen. That was a 2. And this is of our general formula, so that is 2 as well. Okay, so this is what we have, right? Now, we balance this out in terms of CHO already, so we can take this away. Now, I see most of you have said that your answer was D, but now I just want to show you something. We are not allowed now to have a fraction in this balancing. So because we have this 13 divided by 2, we're going to multiply this entire equation by 2. So all of this is going to be now multiplied by 2. So I'll just say all of it is going to be multiplied by, multiplied by 2. So if that is the case, that means we'll have an answer of 2C4H10 plus 13, because remember now 2 multiplied by that will give us just the 13, O2, and that is going to give us 10 H2O plus our 8 carbon, CO2. And that is what we have. But they are asking us, we need to complete the combustion of 1 mole of butane, of what we need at least for this. So in that case, we now need to get this in terms of 1 mole of all of that. So butane is on this side, and this is worth 2 moles of butane. So now again, we're going to have to divide everything by 2. So you're going to say, okay, all of this is now divide by 2. So that will again give you your, so the same reaction that we have on top, all right? But when you do that, 13 divided by 2 is actually 6.5. Everything else is going to be the same as here above. That will again be to 1 mole and stuff. So what they're saying here is the complete combustion of 1 mole of butane needs at least 6.5. So if we look at our options, 18 is, we have 5. It can't be 5 because you see our value was 6.5. It could be 7, And 13 is also a big number. So the one that's closest to 7 is C. So your answer here is actually C, guys. So I think I know where most of you guys got D, because you saw the 13 over there. You multiplied everything by 2, and then you got your values, but the answer is actually C for this section. Okay, now moving on. 1.5. The Maxwell-Boltzmann energy distribution curves below show the number of particles as a function of the kinetic energy for a reaction at 4 different temperatures. The minimum kinetic energy needed for effective collisions to occur is represented by E. Here is our graph given. Which of these curves represents the reaction with the highest rate? Is it A, curve A, B, curve B, C, curve C, or D, curve D? So, in this particular case, remember you guys can type your answers in the chat. So you're going to look at the graph, you look at that sections, then you're going to see, okay, you have your number of particles and your kinetic energy. Then you have your activation line as well. So in this case, if you're going to try and see which one represents the highest rates, answers in the chat, please. Okay, there I see your answer. I'm not going to say it out loud. I just hope that no one copies each other's answers. There we go. So in this case, here you'll see that this is our activation energy. No matter how many particles you have, remember that's the height of the graph. No matter how many particles you have, that does not mean you will always have a reaction. Only if your activation energy, which goes from the bottom all the way to the top, right? Well, sorry, only your activation energy, which is this line over here. For the top of your curve is on the right-hand side of that line, right? That is where you have your rates, and they are actually making more product. So it is not A, because on the left-hand side it's not B, it's not C. The answer is D. So you are correct by saying the answer is D, right? That has the highest rates because it actually met the requirements. Remember, activation energy is the minimum amount of energy needed for this reaction to take place. And that is our D. 1.6. The graph below shows the changes in X, Y, and Z over time during a reaction. And this is given over here. Which of the following balanced chemical equations is correct for this reaction? And then they give these different options. So this is a hypothetical question, or at least a hypothetical equation. As you can see, there's X, Y's, and Z's. It's not like water and all of those different parts. So in this case, and at least they're telling us it is balanced. So we know, okay, it's balanced, that's good. So here we need to use the graph to find out. So what you should do here is they tell you use the graph, and they told you it is the changes of your reaction over time, right? So how this actually changed throughout the section. Thank you. I see you guys answering nicely. Now in this case, we'll start from the top line, or at least the first line in our graph. You see it begins by 2.5 and it ends over here. Now, if you go in line with that, it ends here, which means for X, from where it began to where it ended, it started by 2.5 and it ended at 2, which means if we minus those two from each other, so for X, if you say your 2.5 minus 2, we know it's going to be equal to 0.5. Now, let's look at Y. We will erase. Next color. Y also began here. So Y began by 2.5 and it ended over here. So that is at this point. So that is 1.0. So for Y, that is going to be our 2.5 minus 1. And that is going to be equal to 1.5. Then erase, and we do our last one over here. Because remember, we want to see how these are changing with each other. So I'm going to now choose, let's go green. This began by 0. Now remember, this is a product, that's fine. And it ended over here. This is at 0.5. So by how much did that change? Z, I'll just make a line like that so it doesn't look like anything else. Z is equal to 0.5. Now you check the ratios between all of these. So erase these at least. So as you can see, when it comes to our X, Y's, and Z's, our X and our Z both is 0.5. But if we take X and if you multiply X by 3, that will give you 1.5. Because remember, that will be 0.5, 1, and 1.5, which means our reaction is going to be A. Because this would be a 1:3:1 ratio. This is where you get, they are the same value, so 1:1, and this is by 3, because 3 multiplied by 0.5 would also give you 1.5. Perfect, and that's how we got that answer. Moving on. 1.7. HPO4 2- is an ampholyte. Now remember, ampholyte means it could be an acid or a base. Which of the following pairs represents the conjugate acid and base of HPO4 2-? And then they have given you this table. They give you A, B, C, D, and then which could be conjugate acid, which of these could be conjugate base. Now, when we do this section, remember, a conjugate acid, I'm going to write as Ca, because remember, I don't want to take too much time. Conjugate acid is the opposite of conjugate acid is a base. So that's a B. And if you have a conjugate base, which is Cb, so conjugate base, marker, will give you an acid. Now, the way that I like to remember this is AdBa, AdBa, where an acid donates a proton. So that means if an acid donates a proton, it will give away a H plus, right? So that's how it will be. And then basically it will, still with this part, it will also become negatively charged. So that's how we know AdBa. Base, AdBa. So that's, sorry, that's supposed to be A. So AdBa. AdBa. When you have a base, that would then mean it is going to accept your proton. So it's going to gain in hydrogens and with a positive sign. So that's how we're going to look at this. All right. So these are what we're going to be focusing on. Now, if they want us to deal with this part here, that means we are going to have to see, okay, if it is HPO4 2-, right? In that case, if we want to think of this as donating a proton, remember, acid donates a proton. Acid is going to give away a hydrogen, so you'll lose a hydrogen, and it will become more negative. So if that is the case, you lose your hydrogen, so you don't write your H, so it'll just be PO4 3-. And that is going to be when it is an acid. Then we move on. If we have it as a our H PO4 2-, and if it's a base, it's going to accept a hydrogen, so that now is be more hydrogen. So it's H2 PO4- only, because remember, you gave that other one away. So that is now going to be when it's a base. But in this cases, we are speaking about conjugate acids and conjugate bases. So we know the acid, as I said on top, the opposite of it is our conjugate base, so our Cb, and our base, the opposite of it is a conjugate acid, so that is Ca. So now we look, where is our conjugate acid going to be this? And where, so basically let's look at that. It is going to be in, it could either be B or C, right? B or C. And where is our conjugate base going to be? This one. That is going to be B. So our answer is B. And that's how we got to this. Right? So you see how we had to break it down by all of those definitions. Right? They try to trick you with using the conjugate acid and the conjugate base. But I hope you all understand how I got to this answer. Now, moving on. 1.8. If the concentration of a sulfuric acid solution is 1 times 10 to the power negative 3 moles per decimeter cubed, what will the pH of your concentration of your hydronium ions of the solution be, respectively? And then they give you this. So remember, type your answers in the chat, please, just to have the engagement. But here they're telling us the concentration of our sulfuric acid. Remember, that is H2SO4. But also, because you're speaking of the acid, we know that is our H3O plus ions, right? So we can also write like that, the concentration of this. And they told us it's 1 times 10 to the negative 3. So in this case, we can go and we write down it as, we know our formula for pH is equal to negative log of the concentration of your hydronium ions, H3O plus ions, which is in this case, the concentration of our sulfuric acid. So that means you're going to write as negative log of 1 times 10 to the negative 3. Right? If you are going to type that in your calculator, you'll get the answer of, it should be 3. That's correct. 3. All right? In this case, your options in your table is by 2 decimal places, and they have it as 0.0. So, okay, 3.0. Now we know our answer could either be C or D. Now, how are we going to calculate the concentration of our hydronium ions? Well, we know we have our Kw formula. Now, Kw is your equilibrium constant for water. That is equal to 1. Well, yes, basically, let's write it out completely. That is actually our H3O plus ions multiplied by our OH minus ions, right? The concentration of both of those. Now, our Kw formula is actually 1 times 10 to the negative 14 is equal to the concentration of our hydronium ions, and that was given to us. That was 1 times 10 to the negative 3. And then we have our OH minus ions. That means we are going to have to now say our 1 times 10 to the negative 3 is going to divide our 1 times 10 to the negative 14 to get the concentration of our OH minus ions. So you're going to divide your Kw by your concentration of your H3O plus ions, and that should give you an answer of 1 times 10 to the negative 11. So here we have our pH as 3, and this answer as 1 times 10 to the negative 11, making our answer D. Yeah, I see you're asking, where do I find that? That is a constant. So your Kw formula is always 1 times 10 to the negative 14. Another way you can think about that is, this is using, we normally use your logs and things. Basically, let me put it like this. For pH, is equal to 14 because of your 14 in your Kw formula, right? When it's neutral. This, in general, when it's at neutrality, it's 1 times 10 to the negative 7. And your hydronium ions would be 1 times 10 to the negative 7. Both of these will be equal to each other because it will be neutrality. If that number of your hydronium ions increases, you have a stronger acid. If the numbers of your hydroxide ions, which is OH minus, increases, you have more of a base. When they are equal to each other, which is 1 times 10 to the negative 7 and 1 times 10 to the negative 7, it will be neutral, which will be equal to 1 times 10 to the negative 14. So that's why we have a pH scale of 14. And like someone else also just said, it's on the formula sheet. I could have said that as well, but I wanted to explain why we got that. Moving on. Oh, that was just for me to write down more calculations. Moving on to 1.9. Which of the following containers can be used to store an iron 2 sulfate solution? Is it going to be A, aluminium, B, magnesium, C, nickel, or D, zinc? All right, so is our iron 2 sulfate solution going to, which of these following containers can be used to store iron 2? Now, from here, you can see iron 2, so that's going to be Fe2 plus. That's what you're going to have to look out for. All right, so we're going to be dealing with this. So, okay, now, in this case, we now need to see where we find Fe2 plus on our table 4A or table 4B standard reduction potential section. So we are going to be focusing on aluminium. So you can see it's going to be aluminium, magnesium, nickel, and zinc. And we're going to see where all of these fall in relation to our Fe2 plus. Now, for this one, it's a bit difficult normally to just put this picture on here because otherwise you're going to have to zoom in and see what happens. So what I'm rather going to do is I'm going to stop sharing my screen. And then I'm going to move on to this over here. Yeah. There we go. So perfect. As you guys can see, that's good. Now, reason why I say that is because in order to place this on your screen, do you see how long the table is? Now, I'm not going to go into a full lesson, otherwise it's going to take too long. Remember, you could either use this table 4A or table 4B for this reactions. I can, let me do more. Where's my mouse? There we go. I'm just going to zoom in a small bit more so you guys can see a bit more clearly on your screens. Now, remember, we want to see this in relation to our table. Is this the highlighter? Yes. With Fe2 plus. So this over here. This part over here, right? Fe2 plus. Don't worry about that other line that just showed up. We are worried about this over here. Let's rather draw. That might help. So the four that we dealt with now was aluminium, magnesium, nickel, and zinc. Right? Those are the four that we're going to be focusing on. Let me just check again. Aluminium, magnesium, nickel, and zinc. That's correct. So I'm just going to go back to what I had. Okay, so I'm back on the screen. So, okay, when we go to aluminium, right, we can see where is aluminium found. Aluminium is over here, this. Right, so right now, okay, we see that is actually above our Fe2 plus. So that means actually more reactive. So we can't put that in there. Right, now we move on to our magnesium. So where do we find magnesium? We'll go look. So magnesium. So this is table 4B, just so that everyone is following along as well. Here we have magnesium, it's just above that actually. So that is negative 2.36. The next one was nickel that we had to deal with. Nickel is over here. And then finally, we have our zinc. Zinc is over here, Zn2 plus. So do you see, right now, you can even see on the left-hand side, the further you go down, it will increase in this oxidizing ability, right? So everything on top is going to increase in this reducing ability. So it's way more reactive. See, if you were going to put this Fe2 plus inside of a container, anything above it would be more reactive. So that means it would have dissolved. If we had to put this iron inside of any of those metals, it would have dissolved. So the only one that is not above it is going to be our nickel. So that means it is safe to place our Fe2 plus inside of our nickel container. So yes, that is what we have over here. Now we'll go back to our slide. Okay, can everyone see again? Good. Let me just put thumbs up. Everyone can see as well. Okay, it is open as well so I can see. Okay, so that is it. Now we move on. So for this, the answer is going to be C, nickel. And you saw how we got there. So that's going to be nickel. Moving on. Consider the following reaction which takes place in the galvanic cell. This is going to be with our chromium as well as our tin, Sn is tin, and this is going to be the form that we have, right? The net cell potential in voltage when the cell reaches equilibrium will be either positive 0.56. It could be 0, it could be negative 0.26, or it can be negative 0.56. And this is what we have over here. So answers in the chat now to see what is going to be the net cell potential in voltage when this reaches equilibrium. Okay, let's just go through the chat as well. Okay, yes, I see you guys speaking about the acid as well. Yes, it's a very strong acid, sulfuric acid, right? Okay, yes, yes, yes. Okay, I see this answer for A, this answer for B. So in this case, as you can see, it was quite a bit crazy to get to that table 4B. But what you're going to be doing here is you will then say, you're going to go for your chromium, you go check your voltage for chromium, and you're going to check for your voltage for your SN, right? You're going to minus those two from each other because that is going to be, you will find the formula on your formula sheet as well. You minus it from each other, and you'll actually see that you get the answer of 0. So your answer here is just going to be 0, right? Going to be 0. So the answer here is going to be B. So, okay, moving on. The letters, or question 2 now, organic chemistry. The letters A to F in the table below represent 6 organic compounds. So here we have this over here. Now we can see that A and B, or at least C, D, and E is all in the structural formula. When answering these questions, the best way is in order to have everything in a structural formula. So I'm going to now write down A. So A will be in red. So we'll write down the CH3. So this is going to be for compound A. For CH3, it's going to be C with our 3 H's, 1, 2, and 3. Then it's CH2, so I CH2. And then you move down to CH2 again. And then we had a CH3. There are 4 carbons, so that is butane with just single bonds. Then compound B, we'll just change the color. So I'll make B, circle B, so we know what we are speaking about as well. So that's going to be B. So butanol. So but we know it's going to be 4 carbons, meth, eth, prop, but. The Al at the ends means an aldehyde, which means our double bond O group is at the end of our chain. So that's going to be, it can either be on the right-hand side or the left-hand side. I'll just write it on the end. Do not number it because it's always found at the end of the chain. So let's see, double bond O. So that's 1, 2, 3, which means there's 1 bond left, so it's H. 1, 2, 3, 4. So now this will be our H here. This will be our H here. 1, 2, 3, 4. That's correct. Our H, come on, our H. H. And this is going to be our structural formula for B. So now at least I have the structural formulas A, B, C, D, and E. When it comes to F, you can see there are it's written C, X, H, Y, O, Z. So we don't know what that structural formula is, so we're going to have that as well. Okay, yeah, I see people asking, is there a way to make the screen bigger? What you could do, guys, is also you could click on the picture of my screen itself. So not where you're seeing my face, because if you click on my face, you'll just see my face big and then the writing small. Click on where you see the actual PowerPoint. That might make it bigger, right? So just check that out as well. Yes. Okay, so, okay, and I see you guys can still hear me as well. So, okay, now we have the structural formulas. Once we have that, we could then answer the questions. Now, here it asks from us. 2.1, is compound A saturated or unsaturated hydrocarbon? Give a reason for the answer. I remember when it comes to saturated, that means all your bonds are completed. Unsaturated means it will be a double bond or triple bond molecule. So they are speaking about compound A. So if we go back, we go look at our compound A. Does all carbons have 4 bonds? Like that's there, that is attached? Yes. Is hydrogen attached only by one bond? Yes. So therefore, we know compound A is a saturated molecule. So there we will say it is saturated because we have only single bonds between our carbon atoms. Please, guys, another thing you need to remember is that when it comes to saturated and unsaturated, remember it's only speaking about hydrocarbons. Because if you have a double bond between a carbon and oxygen, that does not count as unsaturated. It's between carbons and carbons. That's when you speak of unsaturated and things like that, right? Between two carbons. Okay. 2.2. Write down the letter or letters that represents each of the following. So if we have a ketone, well, instead of me just running back to that other slide right now, here we can see, we said this was an alkane. This was an aldehyde. This one has an OH group, so we know it is an alcohol. This has halogens attached, so it is an haloalkane. We don't know what F is yet, and they're not asking us about that, so we don't have to worry. It's only with one mark. So it leaves only E. But is it really a ketone? Well, we see we have our C double bond O group within the chain. It's not at the end. So therefore, we can say the answer is E. Moving on. 2.2.2. Which letter is going to be a haloalkane? Well, we actually just went over it right now. But here you see your attachments are a halogen. Remember, halogens could be bromine, chlorine, iodine, or fluorine. We have bromines attached over here, so we know it's going to be compound D. Moving on. 2.2.3. Write down two functional isomers. Now remember, functional isomers could either be when you have your aldehyde or your aldehyde or your ketone that is with each other, or carboxylic acid and an ester with each other. The reason for that is a general formula is going to be, let's say for instance, the aldehyde and ketone will always be CnH2nO. For a carboxylic acid and an ester, it will always be CnH2nO2. So those are always interchangeable with each other. Your aldehyde and ketones and esters and carboxylic acids. So whenever you see functional isomers, think of those two groups. In this case, do we have the esters and the carboxylic acids? No, so we don't have to worry about this. We're speaking about this one then. We have an aldehyde and we have a ketone. So your answer is going to be B and E. Moving on. 2.3. Consider compound C. 2.3.1. Is compound C a primary, secondary, or tertiary alcohol? Give a reason for the answer. So now to compound C over here. If they're asking primary, secondary, tertiary, you go see where is your OH group and to which carbon is attached. Well, it is attached to this carbon. Now, how many other carbons is that carbon attached to? 1, 2, or 3? There's a 1 here. That is not a carbon. That is not carbon. So because it's only attached to 1, our answer is going to be a primary alcohol. That's also why you only get a primary, secondary, tertiary alcohol, because remember, carbon only make 4 bonds. So the reason for this is that the carbon that is bonded to your hydroxyl group is only bonded to one other carbon. So that's where we get that answer. 2.3.2. Write down the structural formula and a IUPAC name of a chain isomer of compound C. So, okay, write down the structural formula and a IUPAC name of a chain isomer. All right, so that means here we have, this is compound C. Now, remember, isomer is when you have the same molecular formula, but then depending on what type of isomer, it could change as well. We just spoke about the functional isomer. That leaves two other isomers, which is your positional isomer, and the other one is your chain isomer. If you have a positional isomer, all you have to do is you take your functional group and that is when you're going to move it to a different carbon, like a different part on the main chain. Like for instance, in here, we have our carbon attached, or at least our OH group, which is our functional group, attached to this carbon. If we would then just move it to this carbon, well then, hey, that now would have been a positional isomer, or well, no. Let's put it in the middle one, part 2, to make it a bit easier. Right, part 2. So I'll take the other one away. But that is not what they're asking from us. Let's erase. They're asking us for a chain isomer. So for a chain isomer, that is going to be when you're going to take one of your branches, that's not now going to be a functional group, and now just add it to the main chain instead. So that's why it's a chain isomer, right? So branch, go to the chain. Or it could be when you take from a chain and put it into a branch. So in this particular case, we're just going to take that attachment and we add it to the main chain. And this is what it's going to be, right? And that is going to be our structural formula. If we need to write down the IUPAC name for this, remember you always put your functional group on the lowest carbon. So we start counting from there. So that is now going to be for this carbon. How many carbons do we have? 1, 2, 3, and 4. So that's meth, F, prop, bute. So that is going to be butane. It was on the first carbon, so 1-ol. And that is the IUPAC name for this section. 2.4. Write down the IUPAC name for compound D. So it is this one over here. Remember, when naming compounds, always start by counting your longest carbon chain. So if we start counting like this, and you want to get your attachments on the lowest carbon, so we could start counting like this: 1, 2, 3, 4, 5, 6. But now remember, you can't go back in your carbon chain. So, okay, that is how you get one over there. But if we take this and we take this away, and now we go back, pen, and if we rather start counting downwards, 6 and 7, do you see that's a long chain? So please do not fall into that trap of just counting the long main chain. Always look at all your different options, and remember, you can never go back. Now, this is a 7-carbon chain. So it's going to be meth, eth, prop, bute, pent, hex, hept. So it's going to be heptane, because there's no other functional groups. We have halogens, but halogens is added to the start of the name as a prefix. So where do we find the halogens on? We find it on carbon 2 and carbon 3. But now, because there are 2 carbons found over here, it will be called dibromo. And on which carbons do you find it? Carbon 2 and 3. Now remember, you always separate your numbers with a comma, and you separate, so basically you separate 2 numbers with a comma, and you separate a number. So in this case, starting from the front, it will be 2.3 dibromo heptane. Oh yeah, sorry, I forgot about my other attachment, the part that's not in your main chain, which is now, of course, this. That is found on our 5th carbon. And then you look at the sections over here to see how you write it out in order. Our B and our M. Bromo comes first and our M comes second. So yes, do not forget to count the attachment as well. But that is 2.3 dibromo heptane. Yes. Yeah, don't worry about that. Just remember, when I say don't worry, I mean like the naming. I saw you wrote as 6. Please always write it down first, and then you see. Then you write it what you then you write down your answers, right? So I see someone just had to change the number a bit. So always number it there. Someone asking about the previous question. The previous question, this was the answer here, right? So this comes first, right? So this is going to be butane 1-ol. If you didn't know, but for everyone else, just remember this lesson is being recorded, so I do not want to go too much to the back. Otherwise, this lesson is going to run really, really long. So you can always just rewatch this video. And don't worry, you have enough time before you write on Monday. Where does the meth come from? This is because it is a methyl group. This part over here, methyl, where is it? Marker? Yeah. Remember, whenever you end in "-ile", it means that it is an attachment. So you'll have, if there's only 1 carbon in your attachment, it's going to be methyl. If there's 2 carbon, ethyl. 3 carbons, propyl. And that's where it comes in, right? Perfect. Now, 2.4.2, name, or here you need to write down the name of the functional group of compound B. So that's going to be of compound B, which is this. Now you might think, oh, hey, that is an aldehyde. Then you write down the aldehyde. Please do not do that. They are not asking you, what is this homologous series? you have to know your definitions and what each of these scientific terms means when it comes to this exam, because they can try and trick you with that. Because that's what some people would have written, maybe, aldehyde. But they're asking for the functional group. So remember, that is your C double bond O group. And that is what we call a 4-mile group. If they ask you the functional group of an alcohol, which is the OH group, remember, your hydroxyl group. It ends in YL. As you can see, it's an attachment. So please make sure about that. Oh yeah, I see someone's asking if butane 1-ol, if you just wrote it as butanol, if it'll be wrong. To be honest, it shouldn't be wrong, but to be extra sure, please write it as butane 1-ol, just so that they know what you mean as well. Right? But it shouldn't be wrong. But like I said, just to be extra sure, because you want to know you get all your marks properly. Try not to take any shortcuts or anything. Okay. 2.5.1. So, okay, here it says, a sample of compound F contains 40% of carbon, 53.3% of oxygen, and X% of hydrogen. So we don't know our hydrogen. So what we're going to do here is we are going to now write down what we know. Always do that. Don't just highlight and then move on further. If you write down what you have, it will make it a bit easier. So we know. So we have 40%, or at least let's just say carbon is equal to 40%. Oxygen is equal to 53.3%. And hydrogen is what? We don't know. Then that says in 2.5.1, if the molar mass is 60 grams per mole, calculate the molecular formula of compound F. So, okay, that's what we need to do. Now, whenever you see percentage, by now you even know this from mass, whenever you see percentage, you know it's that number divided by 100. So that means all of these is now, so that means for carbon you have 40 divided by 100. Oxygen 53.3 divided by 100, which means for hydrogen you'll have X divided by 100. Now, down now, in most formulas, even like when you write the general formulas down, you always write as C first, then your hydrogen, and then any other attachments such as oxygen, your OH group, your halogen, all of that. So I'm going to write in terms of that instead. So I have that C, H, come on, H, and O. I'm writing in terms of this. So here we said this will be by 40. Hydrogen, we don't know. All right, hydrogen, we don't know right now. And wait, let me go back. Let me go back so you can follow a bit better. Let me go back. I actually just jumped a bit there. So before we get to this, because we want to find out what hydrogen is. So as I was saying, all of these is divided by 100. So that means we can take this and we are going to write now to calculate hydrogen. It's going to be a 100, because remember it's by 100%. And if you're going to, it will be minus by the sum of these two, 40 plus 53.3. If you're going to type that in a calculator, you'll get an answer of 6.7. And we're still dealing with percentage. So now we know that hydrogen will actually have 6.7%, whereas oxygen is 53.3 and carbon is 40%. Right. Now that we have it like this, so these are our values. Just remember 40, 53.3, and 6.7. So I need more space, so I'm going to write on the side now. I told you in terms, we're going to write it as our C first, our H next, H, and our oxygen. We said our carbon was 40%, so we write it as 40. Our hydrogen was 6.7, that we just calculated, and our oxygen was 53.3. Now, when it comes to this, you take that your entire substance is worth 100 grams. And if that is the case, if you're in your total of if the total mass of your substance is 100 grams, that means 40 divided by 100, which is your carbon, that 40, basically the 40 in that substance will be carbon. 6.7 will be hydrogen, and 53.3 will be oxygen. So that is going to be like your mass in that formula that you have. So now from here, we can calculate the number of moles. And we know the formula for number of moles is N is equal to mass divided by your molar mass. So we are going to say these are the masses of the compounds. So that is 40, hydrogen's mass is 6.7, and oxygen's mass in this case is 53.3. Now you're going to divide it by its molar mass for each of these. If you go and you look on the periodic table, you will see that your carbon's molar mass, the number at the bottom of your carbon, is 12. So you're going to say 40 divided by 12. Hydrogen's molar mass is 1, and oxygen's molar mass is 16. Then, if you're going to write that in your calculator, now for carbon, it is going to be an answer of 3.33. For hydrogen, if you say 6.7 divided by 1, it will still be 6.7. Right, 6.7. And then for this case over here, we're going to have it as, if you divide that, it will also be 3.3. Now we have the number of moles of everything that we have. But this is not what they're asking from us yet. When you get to this spot, you now need to divide all three of these by your lowest number. So what is our lowest number? 3.33. So we're now going to divide this one by 3.33. We're going to divide this by 3.33, and we divide this by 3.33. 3.33 divided by 3.33 is still 1. These two divided by each other will give you 2, and this divided by each other is going to give you 1. Now what you do is, you take your element, and the numbers that you just got now will be a subscript. So that means it will be C. The subscript is 1, so you're just going to write it as C. The subscript for your hydrogen was 2, so you're going to write it as H2. And then our oxygen subscript was 1, so we're just going to write it as O. But now, let's look at what the molecular formula is of this. If we have now, so I'll write down the molecular formula for our C, come on, CH2O is equal to, there's only one carbon. The molar mass of carbon, as we said over here, is 12. So you write that's 12 plus 2. The molar mass of that is 1. So we write that here. Plus our oxygen, there is 1 oxygen, and its molar mass is 16. If you're going to type all of that in your calculator, you'll get an answer of 30. And because it's molar mass, it is grams per mole. But this is not what we initially want, because if I move back, here it said, if the molar mass of a 60 gram per mole of this compound, right? They basically said the molar mass is 60 grams per mole. We need to calculate the molecular formula of F. But in this case here, they're saying it is 60. What did we get for our answer? We got 30. So we know, hey, that can't be right. So now what you do is, you take the 60 that they said, you divide it by the answer you had, which was 30. That's going to give you an answer of 2. Now you take this and you multiply it for each element here. So carbon multiplies. So instead, you're going to have your C multiply now by 2. So now it will be C2. That H will be 4, and this O will be 2. That will give you the molecular formula of 60. If you do not believe me, this 2 would be the same as now just saying, replacing all of these 1s with a 2. And remember now, just doubling all of that will double this answer as well. So this is going to be the molecular formula that they asked for compound F. And if you look over here, it was also written it in form of C, H, and O, just like we had it. And all of that was worth 4 marks. 4 marks. Very nice question. Now, okay, yes. Okay, yes. Okay, so here we have, yes, 2.5.2. Write down the IUPAC names of the two organic compounds that will have this molecular formula. So still speaking of compound F, so speaking about that, so we'll just go back quickly. I had that C2H4O2. So I'll write it here as one C2H4O2. Right? So we're going to have it like that. And here, so we need to write down the IUPAC names for two of the organic compounds that will have this molecular formula. So we'll have the same. It is going to be ethanoic acid, because we know it's dealing with two carbons, and we know ethanoic acid always deals with, here we go, C double bond O, OH group. So that is going to be where you have your nitrogens already. You're going to have your carbon, your second carbon that you have. You're going to have one hydrogen, hydrogen, and hydrogen. And if you count all of that up, it's going to be 3, 4 hydrogens, 2 carbons, and 2 oxygens. Now, remember I told you that what normally follows the same formula of a ethanoic acid, sorry, of a carboxylic acid is going to be an ester. That also is CnH2nO2. So in this case, we'll also write it, oh, sorry, suppose to write it there, 2 organic compounds that will have that. So the other one would now be a ester that has that 2 different carbons, right? That's going to be your second formula that you're going to have, or at least your second organic compound. Okay, so moving on. Question 3. The table below shows the boiling points of 4 organic compounds represented by the letters A to D of comparable molecular masses. So here's compound A to D. They are all as IUPAC name. Its molar mass is given already, as well as its boiling points. But here we can already see, yeah, we're going to have a problem. They say X or Y is going to be the boiling point of D. So we know they're going to ask us a question about that. Compounds A and B are structural isomers. So that means both of it has the same molecular formula. You find the exact same carbons, hydrogens within both of it. It's just spaced out differently. How the structural formula looks is going to be different. 3.1.1. Define the term structural isomers. This is the more scientific way to place it. As you can see, this is worth 2 marks. And do you see? I have underlined the parts where you will get your marks. Please memorize this word for word. That's where you get your marks from. Some of these questions you won't be able to predict when it comes into the exams. Like you won't know which molecules they're going to give you, which organic reactions they're going to give you. But what you can predict is your definition. So please go over it word for word for each topic. 3.1.2. The boiling point of compound B is higher than the boiling point of compound A. Explain the differences in the boiling points. Now, whenever you have two different compounds, don't just place those two next to each other. What's going to happen is you're rather going to write like this. So I'm going to first write down my compound A, just so everyone can see. So I'm going to start off by this part of here, butane. So that is compound A. Meth, eth, prop, but. Then we added as 2.3 dimethyl. So we have 2 single carbon chains that's attached to this. 2 single carbon attachments. So that means they're on carbon 2 and 3. So it can be over here, C, H, H, and H. And on 3, so that could be over here, C, H, H, and H. There are hydrogens everywhere else. But now, instead of just wasting time, you guys know that there are hydrogens here. Change the color. B. So we'll make B because we are comparing compound A and B. So what is B? B is this one. B, hexane. Meth, eth, prop, but, pent, hex. So that's 1, 2, 3, 4, 5, 6. If you look on the side, 1, 2, 3, 4, 5, and 6. Both of it has 6 carbons. And then there are just hydrogens everywhere else. Bam, bam, bam. Hydrogens all over. Now, when it comes to this part over here, if you are going to compare these, remember, you bring these molecules as close to each other as possible, right? The closer to each other it is, the stronger the boiling point will be. Because as you can think about it as more attracted to each other right now, as okay, let's not use that word, otherwise they might be like, hey, the different forces and stuff, you're not deal with that. Just know that the closer your molecules is allowed to go to each other, the harder it will be to break it apart from each other. If you are going to bring another hexane molecule directly next to that, where's my mark? Where's my mark? Yeah. So that means your other carbons would be directly here already, with its hydrogens, of course. Whereas, do you see here you have these branches? It will be the other carbons might be up here, and then this one will also have a branch. Look how far away these will be to the actual main chain branch. So this is weaker. More branches, weaker intermolecular forces. So therefore, we can say, if we take all of this off the slide, that whenever you compare things, always answer it in this order. You need to state, which terms, you need to state which compound you are speaking about. You're also then going to then compare, as you can see, there's worth 3 marks, its structure, its type of intermolecular force, and then the energy needed to overcome that intermolecular force. Thank you for writing that answer. So in this case, in which terms am I speaking? I'm going to be speaking in terms of compound B. You could write hexane if you want to. So you don't have to now write everything on the left-hand side. That is just a guide from me to help you guys out to answering these questions. So what you would actually write down on your paper would be, in terms of compound B, the hexane is optional. Then you can say it has, so for a structure, a larger surface area and longer carbon chain than what you have in compound A. Remember, you do not need to write down its name. As long as you say A or that, they know what you mean. So that means, as you can see, a straight chain that we have, right? We're just speaking of B as a long main chain. The type of intermolecular forces, when it comes to this is going to be, it will have stronger intermolecular forces, because remember, it is closer to one another. But what's the name of the intermolecular forces when it comes to these type of things? Well, it's going to be your London forces, right? It's not going to be dipole-dipole or hydrogen bonding, please, not that. It's your dipole-dipole, or you can say your van der Waals forces. And then, because it has so strong intermolecular forces, that means you're going to need a lot of energy to overcome that intermolecular forces to break it up. You could also write it in the opposite terms. When you speak of in terms of compound A, that means you just write the opposite. It has a shorter chain, or at least it will be a smaller surface area, weaker intermolecular forces, and you'll have less energy to overcome, right? So you could write it. That's why you always say in terms of which one you're speaking about. 3.2, define the term vapor pressure, worth 2 marks. This is it over here. I can't teach that to you. Sometimes you just have to memorize these words. Here you'll see there are 3 parts underlined, but that is still where you're going to get your marks. I know it's not worth 3 marks, but these are the words they are looking for. 3.3, one of the compounds, B or C, will have a higher vapor pressure. Give a reason for your answer. Okay, so is it going to be B or C? So let me check with my, yeah. So, okay, this is going to be compound B, right? And the reason for that is now going to be, it's like I were done with the multiple choice. We were given the boiling point. So which one have a bigger boiling point between these two, B or C? We are speaking about, we are speaking of this and this. So remember, I said higher boiling point equal lower vapor pressure. I know in the multiple choice I had it other way around, but it still means the same. Lower boiling point equal higher vapor pressure. So which one have the higher which one have the higher boiling point? This, which means this will be a lower vapor pressure. This have a low boiling point, which means this will be high vapor pressure. And what they're asking us, which one will have a higher vapor pressure? Answer is B. So the reason for the answer is going to be it has a lower boiling point than C. There we go. And that's where you get your 2 marks. Oh, sorry, I guess I'm going a bit too fast. I'll slow down a bit. Consider compound C and D. So these two now. This one and this one. As you can see, the differences is, of course, is naming. The molar mass is the same, and we're not sure what the boiling point is. 3.4.1. Will the boiling point of compound D be X is equal to 75.5 degrees Celsius, or will it be Y 135.5 degrees Celsius? Write down only X or Y. Answers in the chat, please. So, I'll calm it down a bit. So let's see if you guys get this. So remember, you don't have to write out the value. You just have to say if it's going to be X, which is going to be 75.5, or Y. In the meantime, I will write down the structural formula just in case if you need that. Methyl propanoate, oxygen, in the middle. Whenever I do a carbox ester, I always put the oxygen and then my 2 carbons. Then there's one that will always have a double bond. The double bond is where you get the carboxylic acid. And then I see someone saying, why due to hydrogen bonds? Okay, remember both has hydrogen bonds, but one is stronger than others. But okay, yes, you are right to put that as well. But you do not need to give a reasoning. But the only 2 that deals with hydrogen bonding is a ester, a carboxylic acid, and an alcohol, right? But yeah, I'll just write this down anyway. Methyl propanoate. So our one that does not have a double bond, that carbon is your alcohol. So this is going to be your alcohol section. And then propanoate. So that's 1 carbon already, 2, and 3. That will be our compound D. And then our compound E. Different color. Pentan 1-ol. So that is meth, eth, prop, but. Pent on our first carbon is going to be where you get your OH group. And you have your hydrogens everywhere else. Please do not, please, even though I'm just writing it out like this, do not do that in your exams. You, of course, need to write your hydrogens everywhere else. This is just for you, for your sake. Okay. So in this particular case, so which one is going to be over here? Well, if you're going to look at what we have. Oh, I'm not just writing C here because of the answer. That is going to be, that was just because of the molecule that I had, right? Just know that. And I write this as D, so people do not get confused as well, D. So this was D and that was C. So which one will have? So that means if we have an ester, right? This is the ester over here. All right, if we have that ester, then we're going to see that it has to be higher because of hydrogen bonding. And you are correct. So which one is higher than 79.8? It's going to be 135. So final answer is going to be Y. Just as everyone was saying in the chat as well. Perfect. Now, moving on. Come on. See, yes. Okay, explain your answer. So here it is, right? So this is your answer. And this is going to be where you get your 3 marks. Once again, you state in terms of which structure you're speaking about. You say how the structure looks. You say the type of intermolecular force that is happening there. In this case, C has dipole-dipole, D have hydrogen bonding. Then you say the D, which is hydrogen bonding, has stronger forces than C. Therefore, it's going to take more energy to overcome this. And that's going to be where you get the answers. moving on to question 4, right? So you'll go question 4. Depending on the time, we'll see that I'll try and do question 4 and then question 5, and then we'll take a short break and then we'll go further, right? So in this case, we'll have to look at the different parts that we have for this molecule. So over here, there's going to be quite a lot to get. Let me just check here. Yes. So we are going to split. We are going to split this up into different parts. So I'm going to now just deal with this first part over here. This part over here. All right, this part here. So with blue is going to be what we focus on, because that's going to be with our A. All right, so our C with our H, H, H. Always write down what you have. It will make it a bit easier to deal with. Then we have our CH. So it's only one H over there. And here we have our CH2. So that can be a, come on, H over here. Let's make it maybe H here. It's fine. So there's 1, 2, 3, and 1, 2, 3 for the second and third carbon. So we put our double bond in between there. So that is what this molecule is. Now we move on, just to make sure that everyone does follow along. So that's why I like using different colors. So for compound X, you are adding HBr. So that means we are adding a hydrogen and a bromine. So that means we are going to now place this hydrogen on one side of where we break our carbons and the bromine on the other side. So then we're going to break our carbons, and on one side you're going to have to put a hydrogen, the other side a bromine. Remember, you look at the two hydrogens that you just broke the double bond apart. Then due to Markovnikov's rule, you count your hydrogens. On the left-hand side, you only had 1. On the right-hand side, 1 and 2. So clearly, on the right-hand side has more hydrogens. So due to Markovnikov's rule, the hydrogens is going to go where it has more hydrogens. Where the party is at, right? It's going to go more that side where it's more hydrogens. So that means for our other one, we are going to have our hydrogen that attached here, and the bromine will attach here. So we can take that away, that away, that away, that away, that. In. So it will C, double bonded, sorry, single bonded now. And these are all our hydrogens over here. And this is what we're going to have as our compound X. Right, compound X. It's this one here. Yes. So we're only dealing with that. Now we're going to deal with another one. Change color, maybe purple. It might not be as different. So that's going to be for compound D. And it was given to us already. So let's put the arrow. So if you watch this later, you know what I'm speaking about. CH3. You can also, of course, be doing this where you guys are writing, so that you can remember. It's better to write down so you know what you're doing as well. CH2, 1 and 2. And this one is CH3. CH3. And that was given to us, right? So this is our compound D. When you went backwards, let's change color. Come on. Let's mark it. Okay, let me just move this mouse, sorry. Yeah, so when you go back this way, this is when you have compound C, right? Or at least reaction C. And then this was for reaction A. Okay, so we'll move on now again. This was reaction A. So we dealt with that. Now we're going to deal with the next part. When you're going to have a compound Y, which is methprop, propane, and it's going to give us an alcohol. That's going to be compound B. So I need more space, so I'm going to write that here. Compound X was methprop, which are propane. No. Compound. Sorry. And no one in the chat told me either, guys. Remember, I added HBr. So what actually supposed to happen here was I added the hydrogen on the one side, which means on the other side I had to add my Br. The Br didn't just vanish. So it is 2 bromo propane. So that is compound X. So we go here. So always check your answers, guys. So it's 2 bromo propane. I thought it looked weird. Br was here. Everywhere else was when we just had our hydrogens. So that's over there. Hydrogens everywhere else. Come on. And there we go. This is this compound X, and then using reaction B to make an alcohol. So whenever you want to use that, that means you're going to have to let this reaction undergo hydrolysis. So when water is added or a base is added, remember you want an OH group. So in this case, you can maybe say any type of base or strong base, maybe a KOH, right? Just so that you have this. This will swap places with this now. Therefore, making it 1, 2, 3. Instead, it will now be your OH here. Because remember, they wanted as an alcohol. It was still to us. It was given to us as an alcohol. So that's our OH. And then you have your hydrogens everywhere else. Right? So that is going to be our, now it will be called propan 2-ol. This one was red 2-bromo propane. Okay, now this part here, where they say and alcohol, the minor alcohol product, it gives us this. It's not meaning compound B gave you 2 alcohols and now this alcohol Z is making reaction E. No, no, no. That is not how it works. Because if you look at what is given here, this is actually a carboxylic acid. Sorry, this is an ester. Because look, here you have this weird double O, your 2 oxygens and your 2 carbons next to each other. That usually represents a ester. So I'm going to write this out now for you. We'll take this away, take that away, change color. So this is CH3 and then CH2, CH2. So I'm going to write that down over here. Yeah. So CH3. And then we have our CH2. And then another CH2. Then we were given a OO and then a C. So that means we're going to put our oxygen, our C, and here we have our oxygen. That represents this part over here. This part over here. And now we have a CH2 and CH3. So now you're going to fill that again. CH2 and CH3. Yeah, CH3. There we go. Okay, then. Okay, so all of that now gives us an ester. So this ester, remember the part that does not have the double bond is your alcohol. So how many carbons are there? 1, 2, 3. So it's going to be propyl. So that answer is propyl. The part that does have the double bond is your carboxylic acid, and it's going to have an O8 at the end. So meth is prop. So that's ethanoate. Ethanoate. And this is not done because here you see it was used from there you'll get an alcohol, right? This alcohol helped make this. So now all you do is, in order to find out what alcohol Z was, alcohol Z, you look at your alcohol side. So it's going to be the part that does not have it. So it's this part here. And that is going to be your propanol, right? So that's going to be your propyl. So that means the alcohol for alcohol Z is going to be a propanol. Okay. And I got it from the ester itself. Now, let's see what I asked. Write down the type of reaction that occurs at A. So at A, we have our, let's go back. We have a double bond that's going to a single bond, right? So in that case, we added our HBr, so we broke it apart. So because we added HBr to this molecule, you can think about it that we eventually use addition. And what did we do for addition? Well, we added a hydrogen and a bromine. So you could say you added a hydrohalogenation with the hydrogen and halogen, or you could also write it as hydrobromination if you want to be very specific. 4.1.2. Write down the type of reaction that occurs at the reaction C. So it's the exact same, but now in the opposite direction. So because we had addition going the one way, that means in the reverse direction, it will just be an elimination reaction. Because we see this a hydrohalogenation, the other way would just be dehydrohalogenation, because you're taking it away. And also because we had it as our hydrobromination, dehydrohalogenation, right? Or bromination if you want there. Now, 4.2, write down the name or formula of the catalyst for reaction D. So for reaction D, if we go back up to how it looks, reaction D was this, when we went from a double bond to a single bonded molecule. So we've actually dealt with this in our multiple choice questions as well. So whenever you go from an alkene to an alkane, that will always be like a cracking reaction. All right, so then that's going to be when you are going to, that's a single to the other one. So, but in this case, you'll always use platinum. All right, sorry, wrong question. So we go back. This will be always platinum that you'll use, right? So the catalyst always to go from an alkene to an alkane, you'll always have it as a platinum. Then, okay, yeah, I already gave you the answer, but in this case, for reaction B, it says that it is a substitution reaction that takes place in the presence of water. Write down the type of substitution reaction for B. If you were listening to when I wrote down how we get from compound X to our alcohol, I told you we needed to add water or a base because we wanted OH group. And that, whenever we add water to a salt, we call it hydrolysis. We can write down two other reactions for this reaction. Two other reaction conditions. You're going to use a strong dilute base. And also, you'll always need heat. You could also just write heat or mild heat. Now, 4.3.3, write down the IUPAC name of the major product of Y. I've shown you that on top as well, and this is how it's going to be. Remember, our OH group just takes the place of our halogen in compound X. 4.4, use a structural formulae to write a balance equation for reaction B, showing the formation of alcohol Y. And this is how it can be over here. Right? So we have this. And I've shown you this there on top as well. 4.5. Reaction E is a reaction between minor product, alcohol Z, and a carboxylic acid to form an ester. Here we need to write down the name of this type of reaction. Well, we're trying to form an ester, so that's going to be esterification, or you could just call it condensation. Esterification forms part of the group of condensation. So most of the cases, most people just write down esterification, but this forms part of it. I'm just going to put it inside over there, guys. So, okay, now 4.5.2, name of the inorganic compound formed during this reaction. So in this case, what we're going to do is we are going to write down the inorganic compound. Now remember, the inorganic compound does not have carbon within it. So that is just going to be water. So whenever you join these two, it will just have the one that does not have carbon, will just have water as a byproduct. And here, please, guys, do not write down the chemical formula. If you're going to write down H2O, you will not get the marks. Moving on to 4.5.3, write down the catalyst needed for this reaction. That is going to be concentrated sulfuric acid. And again, please do not write down the chemical formula. So 4.5.4, here you need to write down the IUPAC name of the functional isomer of the ester formed. And that is going to be worth 2 marks. Now this one is not just going to be the ester that we had and we write it down. I want you guys to give me the functional isomer. So for this question, 4.5.4, I want you guys to write, what is the functional isomer of the ester that we made? Here at the bottom, this one. And remember, I can give you a hint again. Remember, functional isomer means so when your ester is related to your carboxylic acid. So answer in the chat. We have seen this paper to you guys, so I hope you guys were actually testing this out and trying it. So we'll see if you actually get this answer. Yes, so yes, you will add your molecules together when you go to an alkane. Yes, that's right. Okay, and yeah, I see someone is saying hexanoic acid. Okay, good. Okay, just saying. Okay, so okay, looks like that's the answer in the meantime for everyone else as well. So if we go back, right, instead of me now writing all that out again, I want to just show you this. Yeah, the ester that we made. Propyl ethanoate. So what you're going to do is you count down all your carbons. So how many carbons do you have in this case? Well, here we have it as a marker 1, 2, 3, and then carry on this side 4, 5, and 6. So that is C6. Then remember that you always now follow with hydrogen. How many hydrogens? We'll just scratch like this 1, 2, 3, 4, 5, 6, 7. I don't know where this mark is, so I'm just marking 8, 9, 10, 11, and 12. So that is H12. And oxygens. How many oxygens? 1 and 2. So O2. So that's what you're dealing with. C6H12O2. So we go back to where we needed. Yes. So here we go. So here we go. C6H12O2. Remember, both of these follows the formula CnH2nO2. So what, because dealing with the ester, what carboxylic acid? We then just have 2 carbons. Remember, C double bond O, OH, that shows the carboxylic acid. We said that we need 6 carbons. So that is 1 already. 1, 2, 3, 4, 5, and 6. Let's count again. 1, 2, 3, 4, 5, 6. Yes. And then here we're counting. So that is C6 already done. Now to do our H12, we're going to count this one already. So I'll just scratch out 1, and here it will be 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. So that is our 12 done. And here's oxygen 1 and 2. Therefore, that means this is going to be our hexanoic acid. And there you can see this is the answer over there. Yes, so the answer is actually hexanoic acid. Please do not forget to write this down. All right, the carbon that we have as well, where your carboxyl group is attached to. This one, all right? So your answer is actually hexanoic acid. 4.6, draw the structural formula of the functional group of a carboxylic acid. Well, I just gave you the answer right now. As always, a C double bond O bond to an OH group. And that's where you get your 1 mark. Question 5. Here it states, this is going to be the last question, then we're going to take a short break, and then we will come back for question 6 to 10. To question 9. There's only 9 questions in chemistry. Question 5. Learners are asked to investigate the rate at which 0.3 grams of impure calcium carbonate will react with an excess of 1 mole per decimeter cubed hydrochloric acid at room temperature to produce carbon dioxide gas. The equation for the reaction is given over here, and that's how the experiment looks. Now, this is not all that is given. You are also given this, where it tells us, so that's the formula. The graph below represents the volume of carbon dioxide produced at regular time intervals. So here we see we have our, just mark it out again. Yeah, So here we see the volume of carbon dioxide that is produced every time, and this is worth the time, right? So it's always over time. And then now it asks from us, we need to write down an investigative question for this experiment. So what we're going to do is we're going to look at what is being compared with each other. We have our volume and we have our time. So we can then just say, what is the relationship between the concentration and the rate of reaction? You could then also state what's the concentration of your carbon dioxide, or at least your calcium carbonate, that is going to be produced over your rate of reaction, so how fast it actually occurs. But I really like this one. And over here, you'll see I once again underlined which of these is the important words you have to have in your reaction. So the one will be relationship and the other one between what? So it's between the concentration and rate of reaction. Now, what is your controlled variable? So you look here and you need to see what was actually kept constant through all of these. So then that will then be our temperature, right? They didn't say anything about temperature over here. It's just the volume that we were changing and how fast it actually occurred. But you could write any of these because when it comes to rate of reactions, remember there are 5 different factors that can affect it. So these are the ones that kept constant. Now, what is the dependent variable for this investigation? Now, before I give you that answer, I'm going to go up and I'm going to put it here on this slide. Looking at the graph, you could immediately know what is a dependent and what is an independent variable. So I want you guys now to tell me in the chat, what is the dependent variable of this reaction? So it's one of the skills you need to have. By looking at the graph, immediately you should be able to know what's dependent and what is independent. Good. I'm glad. I just needed to make sure you guys have that skill as well, because it's very close to the exam, but I want to make sure everyone still have it. And everyone said this over here. So it's actually going to be the volume of the gas that's produced. So the way you look at this is going to be your y-axis. How you remember it is your independent, I remember it as this, it's in the floor, right? It's at the bottom. That's your independent variable. So your y-axis is your dependent variable. It depends on your results that you get over here. So that's correct, guys. Volume is dependent. Perfect. Now, moving on. 5.2. With reference to the graph, how will the rate of the reaction between our time 0 seconds and 20 seconds compare to that with the reaction rate between 30 and 50? So between 0 and 20, there's a marker. So between this one and this one, so how the line is going from here to here compared to when we move to, let's go with green, 30. Come on. Someone was a marker. Here we go, 30. There. Okay, and change the color. Don't know why it's not changing. And green. 30 and 50. So it's this over here. So how it changes from here to here. So here you just basically need to see how the graph actually looks. All right. Is it increasing by a lot? Like look at the steepness of your graph that you have. So in this particular case, you can say that the rate between 0 and 20 is going to be faster than between 30, which is our green line, and our 50, which is our other green line, right? And that is because here they're probably going to ask us what conclusion can be drawn. Okay, let's different one. Between the 60 and 70. So between 60 and 70, here we see that we have it at this point and this point. How is our line? Flat. So what conclusion can be drawn there? Well, there we can just say it was used up. The reaction is done. So we can actually say the reaction stopped. So calcium carbonate, which is our reaction or reactant, right? It was finally used up, and therefore nothing else could occur. Okay, don't worry, we'll come to the equilibrium section. But I understand where you came from with that, but don't feel bad. In this particular case, remember, this is just a rate of reactions. So another thing, always also just look at your arrows, please. So in your arrows here you see that there's only a one directional arrow. So because it's only a one directional arrow, that means it is only making our reactant to product. It's not going products to reactants as well. And then eventually when those are two aligned with each other, that's when they are at equilibrium. So just look at that, but it's okay, don't worry. Now, 5.4, use the graph to calculate the mass of calcium carbonate that reacted. The molar volume is 24 decimeter cubed at room temperature. And this is going to now be worth 5 marks. So we are going to now look at these different values. So what we can decide now is that at which volume did this calcium carbonate finish, basically? And it was here, right? Do we see that? It was at this. Where's my marker? Let's change this color. It's difficult to see this marker. Okay, let's just go with red. So here we see that we just see it in the previous slide as well, at 25. That's when this was done, right? So this was when it was used up. So what we could do is they want to find out, we need to calculate the mass of the calcium carbonate that reacted. And we were given the molar volume. Now we know whenever we're given the molar volume, that is your Vm. We can use this formula, number of moles is equal to your volume divided by your molar volume. And this now is going to equal to, what was the volume of our calcium carbonate that reacted? Well, it was 25. But please do not now just go write 25. Always take note of your units. That could make or break your marks that you get over here in your exams. Do you see? Molar volume is given in decimeter cubed. Our graph is given in centimeter cubed, which means we need to now change one of these. Because they have given us what the molar volume is, let's not change the molar volume's value. Let's change the one from the graph. So that 25, you're going to divide it by 1000 to get it to decimeter cubed. That will give you an answer of 0.025 decimeter cubed. And it's divided by your molar volume, which was 24, as given over there. You're going to write that and type that in your calculator, and you'll get an answer of 1.042 times 10 to the negative 3 moles. That was your number of moles that you have. But remember, this is a 5-mark question. They are not going to now just, please do not think, oh, you sorted one thing out. It was maybe a bit difficult, or at least you had to use a bit of your knowledge to get that answer. Doesn't mean you have to do all of that thinking. Just to get that answer, that is going to be your final answer. Remember, they want the mass of your calcium carbonate. That was done. So right now we have the number of moles. But now this graph is not the graph dealing with your calcium carbonate. I know I said that a bit earlier, but sorry, I made a mistake. This was your graph of your volume of your carbon dioxide. So because this is the volume of carbon dioxide, now we can use this mole ratio, so the number in front, to link it up with the calcium carbonate, which is this over here. So we see as a 1-to-1 ratio. So we can basically say that, marker, here we go. This of our carbon dioxide, number of moles of carbon dioxide is going to be equal to the number of moles of our calcium carbonate, CO3. So what is this? Well, it's going to be, there's a 1 in front of this and a 1 in front of that. So it's a 1-to-1 ratio. Therefore, the number of moles of your calcium carbonate is equal also to 1.042 times 10 to the negative 3 moles. Remember, you can put the moles next to it. I just don't have space on both of those. That's why I'm putting it underneath. Now that we have the number of moles, let's go get more space. So we now need to calculate the mass of our calcium carbonate. Mass is equal to your number of moles multiplied by your molar mass. So we just calculate the number of moles. That was 1.042 times 10 to the negative 3. Then you're going to go to a periodic table and you're going to get your formulas for this. Remember how you do that is there's one calcium, so it's going to be 1 times your molecular formula. That's the number you find under calcium. You do the same for your carbon, 1 times your carbon's molecular formula, and for oxygen, it will be 3 times your molecular formula for oxygen. That should be 16, just for the oxygen one as well, 3 times 16. If you get all of those and you add it together, you'll get a molecular formula for your calcium carbonate as 100. You then multiply these together and you'll get an answer of 0.104. Because we're dealing with mass, that's a small m, do not forget the units. And that should be grams. So you'll have 0.104 grams of calcium carbonate. Oh, yes. I was just checking my answer now. I saw like you had 0.14. Okay. Okay. For someone else, I want me to go back to the slide. If not, there's a slide as well. But I'm guessing you meant the slide. But remember, guys, this lesson is being recorded. So you can also rewatch it again if you are busy writing down. But this is how we got to it. We got our volume of carbon dioxide. We used the formula that was given to us. Then we used this mole ratios to link what was given to us, which was actually carbon dioxide, to our calcium carbonate of what they wanted. And then you eventually got this answer. Okay, that's just for more working out. Now we'll come to this last question within, I think, this question 5. Learners are asked to investigate the rate at which 0.3 grams of impure calcium carbonate will react with an excess of 1 mole per decimeter cube hydrochloric acid at room temperature to produce carbon dioxide. And please, I see you answer that. 5.5. Calculate the percentage purity of the calcium carbonate which reacted in the above reaction. So this, as you can see, is called 5.5, which means we can use the answers that was dealt with in previous questions. So here in the previous one, we saw that the mass of our calcium carbonate was 0.104 grams, right? Is this answer? That's just me underlining that part over there. 0.104 grams. That was our pure sample that we had. Now, when it comes to percentage purity, what is your percentage purity? So percentage purity is equal to the mass of your pure sample divided by the mass of your impure sample multiplied by 100 because it is dealing with percentage. So we multiply by 100. So we just said that the pure sample is what we have calculated. That was our 0.104. Remember, this isn't that times 10 to the thing. That was when it came to a number of moles. That was the grams that we had. And it's divided by our impure, which was given here, 0.3. 0.3. Do not, please, guys, I've seen people make this mistake before. When they forget to multiply by 100. And then you type that in your calculator and you should get an answer of 34.67%. And that is going to be worth 2 marks. And this is how you're going to deal with question 5. Let's just make sure. Oh, there's another question, 5.6. Okay, when it comes to this, here it said that the learners repeat the investigation by using 0.3 grams of the same impure calcium carbonate, but increase the concentration of hydrochloric acid to 2 moles per decimeter cube. Right, so it's going to be this over here. How will the gradient of the graph change when the concentration of the acid is increased? So now we added concentration. So because we added concentration, that means there's going to be a steeper gradient because there's more of this willing to react with what we have already. right? So it will, because it's more, you can have way more things that can be added to it. That can be one of your factors that you add. So basically like increase the concentration, right? So steeper gradient. So that's why you will have a faster reaction that occurs. 5.6.2, use the collision theory to explain how an increase in concentration affects the reaction. And then these three is going to be what you write for your 3 marks over here. Right? So if you increase the concentration, it increases the number of particles, as I said, but this is per unit volume, because remember, concentration is number of moles, which could be thought of as particles divided by your volume. Then that will then lead to more effective collisions that's occurring. And because you have more successful effective collisions, that will then in turn increase your rate of reaction. And that should be question 5. Yes, this is question 6. So, okay, now we are going to take a short break over here. Let's maybe give you about maybe 10 minutes. Let's start at 10 past. Yeah, so 10 past 11. Everyone, please be back. I know it's a short break, but in your exam, you're not going to get a break, but just go take a break. You can go bathroom break. You can go drink something, whatever as well. But then I'll see you at 10 past 11 from question 6 to question 9. Okay, then welcome back, everyone. Welcome back. I hope that everyone had a nice short break. I hope everyone can still hear me. If you can, please use the thumbs up. If you can't hear me, put your maybe you can use thumbs down. Okay, perfect. Just had to make sure. Okay, so now we're going to be moving on to, thank you. Now I'm going to be moving on to question 6. So 4 more questions to go. Now we know when we move on to question 6, that will always be chemical equilibrium. Yeah. So here it's stated, potassium dichromate is formed when nitric acid is slowly added to a potassium chromate solution. The chromate ions, which is Cr4O4 2-, in the solution reach equilibrium with the dichromate ions, as given over there, according to the following balanced ionic equation. And it's given over here from yellow, and it will go to orange. Then for question 1, it asks from us, define the term equilibrium, chemical equilibrium, and it's worth 2 marks. So this is what you'll need over here. Unfortunately, this time I did not underline where you'll get your marks, but here you will say that, I'll bring this now here, chemical equilibrium is the rate of the forward reaction, and it's also equal to the rate of reverse. All right, equals to the rate of the reverse. Right, so that's the 2 different parts that you'll have. Okay, now 6.2. A concentrated nitric acid solution is now added to this mixture. 6.2.1. What color change will be observed in the mixture? Choose from more yellow or more orange. So, answers in the chat quickly, please, and then I'll explain why. Or at least I'll first show, and then 6.2.2 is where we will explain why. Okay, that's correct. Okay, yes. So you're correct, yes. And we can actually see that answer here. In this particular case here, you'll see you have potassium dichromate, which is at the start, is formed when you slowly add nitric acid to it. All right. So when you add nitric acid to this, you will get a more orange color. So in this particular case here, they're telling us a concentrated nitric acid is now added to the solution. So that means we'll just do the forward reaction. So it will become more orange. So I know you guys are just saying orange over there, but yes, we are going to, of course, say more orange, depending on what they asked there, right? They said more this color. 6.2.2, explain the answer in 6.2.1 in terms of Le Chatelier's principle. Now, when it comes to Le Chatelier's principle, just know that whatever change you do to a system, Le Chatelier's principle will always want to balance it out. Because remember, when you have a chemical equilibrium, you have a forward reaction, you have a reverse reaction. Please, that is not when it is at equilibrium. Only once your forward reaction and reverse reaction is happening at the exact same time and the concentration is now constant, that's going to be, that's going to be when you reach equilibrium. So in that particular case, once they at equilibrium, you do a certain change, then Le Chatelier's principle will try and stop it. There's three ways that we could affect it. It's going to be temperature, concentration, or pressure. So in this case, we are changing the concentration, what we have. So here we see that we added nitric acid. Now, nitric acid is a very strong acid, so it will ionize completely. So here we will say that nitric acid ionizes completely in the solution, thereby increasing the concentration of your hydrogen ions. And if that's the case, our forward reaction is going to be favored, so it will now try and decrease the amount of hydrogen ions that we have. Because here you'll see you have your hydrogen ions at your reactants. So then, we then could also say is the concentration of yellow of that ions will decrease, making the entire solution more orange. And that is our Le Chatelier's principle. Relates to that. Now, moving on to 6.3. When the temperature of the original reaction is the original reaction mixture is increased, it is observed that the color of the mixture changes to yellow. Is the forward reaction endothermic or exothermic? And that's going to be worth 1 mark. So now answers in the chat. Is this now going to be more endothermic or exothermic? Okay, so the answer is actually going to be exothermic. And let me show you why. That is because as you're going to increase the temperature, that will always favor an endothermic reaction. But seeing that this mixture turns yellow, which side of the reaction actually goes yellow, forward or reverse, is going to be the reverse reaction. So therefore we say that the reverse reaction is going to be endothermic, therefore making our forward reaction exothermic. Right? That is it. 6.4. Here it now tells us that 11 moles of our first reactant, which is this one over here, and X mole of our hydrogen, which is our other reactant, right? We have that amount of moles initially, are initially added to make a 0.5 decimeter cube solution that is allowed to react. When the reaction reaches equilibrium, so at equilibrium, we will have 9 moles of our product, which is this. Please do not get confused by this and this. I know it looks very similar, but it's not. Here you see we have a liquid. We will not put that liquid inside of our Kc expression. So we will only deal with our 2 reactants and our product. Here it says, calculate the initial moles of our hydrogen ions placed in the container if equilibrium is constant. Calculate the initial moles placed in the container if the equilibrium constant is 0.09. So that's what we're going to be using, right? Just that amount. So, okay, we're now going to write down what we have, and that's going to all be worth 8 marks. So the first we're going to do is, you guys are probably used to this tables and things by now, but we'll use our rice table as R, a ratio, rice. So initial, so RIC change, E equilibrium, but this is in moles, this is in moles, and this is in moles. And then finally, you end up with another equilibrium. And this one is in concentration. So I'll just put it as square brackets right now. Just know that's concentration. Okay, now we'll break our different lines up here. We'll write this across. We only had 3 that we're going to be dealing with, so we can make a line here. Okay, make another line here. Here we see these are our reactants that we will be using. Like I said, is this one, Cr4 2 minus, and our H plus ions, and our product is going to be our Cr2 O7 2 minus, and we're not using the liquid. So I'll write that into my formula that I have over here. So that's going to be CrO4 2 minus, our H plus ions. And then we have our Cr2O7 2 minus. Then now we can go look at the different parts that was given to us. And we're going to fill all of those in. Right, so we have these different parts over here. What? And finally, this line here. Okay, now when it comes to the ratios are the easiest to find. You just write down the number that's found in front, 2, 2, and for this one, only 1. So I write that down. So this was 2, 2 is to 1. That will usually help us find what the change is between all of these. Then it told us that we initially had 11 for our first one, X for our hydrogen, and 9 over here. So 11, X, and 9. So we're going to write that down. 11, X. And now you might think, hey, we're going to write 9 over here. No, no, no. Remember, the 9 is going to be when it was at equilibrium. So it's going to be found down over here. Right, the number of moles that we found was 9. Yeah, the number of moles for our concentration. Moles per decimeter cubed. Don't write it by the wrong place. So concentration is equilibrium is 9, which is this over here. So I write 9 down there. Come on. There we go, 9. But now, that does not mean we don't know anything from our product. You normally would have a reaction, a reactant, and then you have a certain amount of reactants, and then you make products. You have no products, and then you get reactants. So this is actually going to be 0. Right, so we have this over here. So is there any other given information? Well, we know this is our 0.09 is going to be what our equilibrium is at that point. But we were also given this, our 0.5 decimeter cubed. Right, so we know what our volume is. So in that case, we can calculate now. So I'm going to use this slide to calculate, and we're going to place things inside of the slide. Now, here you can see in the bottom right-hand corner, I do not want to make too much arrows and things on here, but in the bottom right-hand corner, you see we have our equilibrium of a product is 9. So we know our concentration is C is equal to N over V. We know that 9 was our concentration. So we can calculate the number of moles. Number of moles is equal to concentration multiplied by volume. They told us the concentration of our product is 9 and our volume is 0.5. We type that in a calculator and you'll get an answer of 4.5. So therefore, that's going to now be our number of moles at equilibrium is 4.5. Now we see, okay, our initial amount of moles was 0. And what do we have at equilibrium is 4.5. Well, how do we go from 0 to 4.5? You add downwards. So we will have 4.5 here because that's by how much it changed. So that means when you went like this, down to get you there, we added. So normally for your products and to your reactants, it's opposite. So that means you're going to minus downwards. for what we have over here. Now, in this case, we can look at our ratio that we have. So now you see here, we have our 2, and here's a 1. So because the change is a 2:1 ratio, or at least a 1:2 ratio, that means now to find the other 2, we're just going to multiply it by 2. So let me erase. You basically, what I mean is you take your change and you multiply by the ratios. You're comparing the ratios together. So now we have our 4.2, sorry, our 4.5, and we're going to multiply that by 2. So that will give us 9 as a change here. Here also, our 4.5 multiplied by 2 will give us 9 as a change here. So what we're going to do now is, because for our products we add downwards, our reactants, the opposite occurs. So you're going to minus downwards. So 11 minus 9 is going to give you a value of 2. And then x minus 9. We will just write that down like normal. X minus 9. You do not need to get all your values right now. We're going to eventually find it out. Now, when we got here, remember we were also given our volume, 0.5. Now we go back. We have a volume over here, sorry, a number of moles, which is 2. So we're now going to take that 2. So our concentration, pen, concentration for your initial reactant, which is CrO4 2 minus, CrO4 2 minus. Remember, this was for a product on top, this is the other one at the bottom. We are going to take that 2 divided by 0.5. So that's going to be 2 divided by 0.5. That will give you an answer of 4. So therefore, your answer over here is going to be 4. Good. Now, for our equilibrium over here, we are basically going to say the concentration for our hydrogen ion. That is going to be our X minus 9 divided by 0.5, which is our volume. And if you type that in your calculator, that's going to give you a value of 2x minus 18. So please do not forget about that middle column. So that's 2x minus 18. And we'll write that over here. 2x minus 18. Is everyone still following along with me? Can you guys give thumbs up? So we have this. Perfect. So this is what we've done with our rice table. All right. So we have this so far. Now, having this, we can plug it into our Kc expression. Now remember, when it comes to your Kc expression, that is always going to be your Kc equal to the concentration of your products divided by the concentration of your reactants. And then do not forget its ratios, basically its coefficients. Remember the coefficients, there's a lot of arrows on the slide, but this coefficients becomes the exponent. So writing all of that down, this is how your Kc expression should look. Cr2O7, this is 2 minus within the bracket still. It was, remember, our product was only 1, right? There was a coefficient of 1. The reactants both had 2 as this coefficient. So that will be to the power of 2. So this is going to be CrO4 2 minus squared. Please do not forget those. That's going to be multiplied by our H plus squared. Yes. Now we are going to write down what was given, not to lose anyone along the way. There's a lot on the slide, so let's just erase. The part I needed to focus on now is, here they told us the equilibrium constant is 0.9. So we're going to plug in those values and all of these values into our Kc expression now. Because I don't like losing people as we move along. So Kc was 0.09 equal to our concentration of our product was 9. Come on. It was just 9. Let's put it in brackets. And then concentration of our first reactant was 4. Do not forget your square. And that is to 2x minus 18. Do not forget the squared. Now, we could just start dealing with this in the calculator format, but what I rather want to do is I want to have all of these. As you can see, this have a square, this has a square. It's not a must to do it this way, but I'm going to try and see what all of these are if you should actually square it. So I'm just going to add an extra step right now. So if you actually say 0.3 squared, that should give you 0.09. And if you say 3 squared, that would give you 9. I guess it is not a must. It's easier to type in the calculator like this. So that's how I left it. So I'm going to deal with everything else as the same. 4 squared. And this is going to be our 2x minus 18 squared. Now, you then rearrange this entire formula. Then, of course, you are going to now divide this by the one side is going to multiply. By now, all of you guys should know how to make x the subject of the formula. If you do make x the subject of the formula, that means x is going to be equal to 10.25 moles. And that is all going to be worth 8 marks. And that was 6.4, question 6. Okay, moving on to acids and bases. Acids and bases, 7.1. A solution of carbonic acid has a pH of 4.2 and the following Ka value, and is given over there. A solution of sulfuric acid has the following Ka value, and is given over there. Before we move on, please, I always want you guys to make sure when you're writing these answers, also always take note of your exponents. Do you see? This has to the power -7, and this is to the power of +3. Don't always just look at the numerical value. Always look at if it's positive or negative as well. Because remember, when you do that, the decimal point would either shift to the right or to the left in your number that you are dealing with. Please, that's an important factor there. Okay. Erase. 7.1.1 for 3 marks. Here it asks from us. Calculate the concentration of the hydronium ions in the carbonic acid solution. So, calculate the concentration of hydronium ions. Hydronium ions is usually your acid, right? So that means, what do we have? We were given pH, so that's good. So we were given the pH of our carbonic acid was 4.2. Now, we can write this into our formula. So we know pH is equal to negative log of the concentration of your hydronium ions. Remember, this is what they want. I also wanted you to know that you could write it like this, or some people prefer this formula where you say your concentration of your hydronium ions is equal to your 10 to the power negative pH. Both of these will work if you should deal with this answers, right? The one on the left-hand side is found in your question paper, in the formula sheet in your question paper. The one on the right-hand side is just a shorter method to do this as well. Whichever method you prefer, you can deal with it that way. Okay, so we were given our pH, which was 4.2. So we're going to substitute that into this formula. I'll be dealing with the left-hand side. So it'll be 4.2 is equal to my negative log of my concentration of hydronium ions. Then we can then say that's going to now be, if I make the subject of the formula, come on, concentration of my hydronium ions going to be equal to 10 to the power negative 4.2. You type that in your calculator and you get an answer of 6.31 times 10 to the negative 5. Because this is in concentration, you write your units, moles per decimeter cubed. And that's going to be where you get your 3 moles. Okay, moving on. Yeah, this is what we have already. 7.1.2. How will the strength of the carbonic acid compare to that of sulfuric acid if both acids have a concentration of 0.02? Write only the carbonic acid is stronger than, weaker than, or the same as sulfuric acid. Give a reason for your answer. So now, yeah, I'd like everyone to write this out over here. The reason why I'm not also letting you do, I'm not asking you to do the calculation questions is because I know some of you might have just fully focused on physics until yesterday, and now maybe you guys are studying for chemistry. So maybe you didn't get to go through the whole paper. So maybe you might not have dealt all the calculations. But these theory type questions, and where you have to use your logic and things, this you might actually be able to understand. Okay, yeah, I see someone is saying that they do not understand 7.1.1. Okay, so we will get to that now. So 7.1.1. They wanted to know that we need to calculate the concentration of hydronium ions. Remember, this is another way of writing hydronium ions, H3O plus ions, in the carbonic acid solution. So you look, so this is solution of sulfuric acid, not that one. This is a solution of carbonic acid. So they want us to focus on these different values. They told you we have a pH of 4.2. So what you do is you go to your formula sheet and you'll see that you have this on your formula sheet. If you look at that, we are given pH. We are given pH. What do they want? H3O plus ions. The concentration of your H3O plus ions. That is what this hydronium ions mean. They did not say hydroxide ions. That's why we just typed in what was given over there into this formula. I think I might know where you guys got confused. Maybe it's where we changed over. When you have a log always is to the base 10. They don't normally write that, but it's usually to the base 10. And then you have your concentration that's on top over here. Now, this is not just log, it's called negative log, right? Now, let's say, for instance, you have this as x, as a hypothetical, right? This is what you have over here. Then what you do is, in order to now to make this the subject of the formula, we, of course, need to get rid of all of these, right? So the first thing you do is, let's say we get rid of this first one by taking the negative over. So your answer will be negative x is equal to your log of base 10. Remember, it's a given, but you normally don't write it, which is to your hydronium ions. Now, to get rid of the log, you basically put this as your exponent to the base. So therefore, it will be 10 to the power negative x is equal to your hydronium ions. And that is why this is also the formula that could be written as. Instead of doing this whole method I just showed you, that's why people came up with this method where you just say H3O plus is equal to 10 to the power negative pH. This means the exact same. Yes. So you see, that's also where we got the, and yes, that is where you get this as a subset of the formula. I hope that breakdown helped you. If not, just rewatch this part of the video, and then might help you out as well. Pleasure. Cool, cool. Now, moving on. Yes. So now, guys, don't forget just to answer as well, and then we're going to see if you get this answer correct. I'm just seeing if you guys are answering, so weak or strong. So, okay, now moving on to this one. Yes. It's okay, don't worry. I'll help you guys out now as we move along. So, like I told you, these values are going to play an important factor. If you type this out on a calculator, you will actually see that this value of your carbonic acid, that is actually a smaller number to your sulfuric acid. Now, what is the small number? It's your Ka value. Now, Ka value is normally showing how strong or weak, so if it will ionize completely or incompletely in water, right? Because remember, you put your acid normally in water and it will break apart and things. So in this particular case, we need to see which one of these two has a smaller value. One is going to be our top one, which is our carbonic acid. Another way you can think of carbonic acid is H2CO3, just in case if you want to write it out that way. But this is carbonic acid. So because carbonic acid has a smaller Ka value than our sulfuric acid, we will say that that this basically ionized incompletely in the water that was there. Because here they want to know, write down if carbonic acid, right, this is the part that we're dealing with, carbonic acid, if it's stronger, weaker, or the same as sulfuric acid. That's a smaller Ka value, so it didn't ionize completely. Therefore, your answer will be weaker than. So yes, you guys have the correct answer. Some of you might have been guessing, but it's perfectly fine. You guessed right. But this is the reasoning as well. I know they say you first write your weaker, stronger, or same as first, and then give a reason. I first wanted to explain and then give my reason. But that's your 7.1.2. Moving on, 7.2. A solution of vinegar can be neutralized with a solution of sodium hydroxide. Remember, that's NaOH. The reaction takes place according to the following balanced equation. There's given over here. The sodium acetate produced during this reaction can undergo hydrolysis. 7.2.1. Define the term hydrolysis. And this is going to be worth 1 mark. I actually, if you were listening very closely to the lesson, earlier I gave this answer as we're dealing with our organic reactions. Remember, I said hydrolysis is basically when you have a reaction, that's when you're going to have water reacting with a salt. And here you can see hydrolysis is the reaction of a salt with water. Okay, moving on. 7.2.2. Will the pH of the sodium acetate solution be greater than or less than 7? So now we look, okay, at that pH, right? Will it be greater than or less than? Well, this is going to be greater than, and let me show you why. Because here they're asking 7.2.3. We need to explain this answer by using a balanced equation. Whenever we mix these together, this is how the equation will turn out. But do you see that? This ends off with a OH minus ions. Now remember, whenever you have OH minus ions, does that mean it will be more acidic or basic? Everyone write that in the chat. If you have more OH minus in your answers, would that make your solution more acidic or basic or alkaline? Just drink a bit of water while you guys. See? Perfect. It will be basic. Because remember, your hydronium ions, which is H3O plus ions, will make your solution more acidic. OH minus ions, which is hydroxide ions, will make it more basic. So in this particular case, we increase the concentration of your hydroxide ions, and therefore it will make it more alkaline, which is also known as a basic solution, and therefore it will increase your pH, because remember, pH goes from 1 till 14. 7.3. An unknown carbonate has a chemical formula of Y2CO3. So there we can already see we have a chemical formula with Y. Most of the time, if you know your periodic table, also if you don't know your periodic table, and you're just used to seeing chemicals together, you don't just see a Y over there. So that means that Y is going to come into play somewhere. And here the question continues by saying, a learner is asked to identify element Y. See? So they're asking you why. Is Y there? The learner adds 0.5865 grams of the carbonate in a conical flask containing 25 centimeter cubed hydrochloric acid solution with a concentration of 0.3 moles per decimeter cubed. The Bayes equation for the reaction that takes place is given over here. The hydrochloric acid is in excess. So there we know. If they tell us that, that means the other reactant is going to be our limiting reagent, the part that's stopping us from making more product. Remember to think about limiting reagents as maybe if you use everyday life, let's say, for instance, you want to make a sandwich and you need 2 slices and 2 slices of bread and 1 slice of cheese. If you want to make that, you go check your cupboard, you go see how much food you have in your cupboard. If you have 1 slice of bread and 1 slice of cheese, it's not going to give you that full sandwich. I know some people will still eat it the same, but in that case, it would mean your bread is your limiting reagent. The bread is stopping us from making a full, proper sandwich. I know some people are still willing to eat it that way, but just to bring that into everyday life, to bring what a limiting reagent is. So with that concept, and I want you to understand this because when it comes to stoichiometry, it's very important for you to know why we calculate certain values first before we deal with everything else. When it comes to stoichiometry, always try and deal with things with your limiting reagent because, like I said, if that is done, then that means your product, you won't be able to get any more product because your reactants, you don't have enough of your reactants to make more products. So your limiting reagent is very important. Anyway, here that's saying 7.3.1. Calculate the initial mole of hydrochloric acid in the conical flask, and this is going to be worth 3 marks. Okay, so even though this is going to be worth 3 marks, there's quite a bit that we're going to have to be doing. So let's get my marker out. We can change the color up. Let's maybe go blue. So, okay, yeah, we were given a few things. They were speaking about hydrochloric acid. So let's look at what we have of hydrochloric acid. We have this. So there we immediately know that our volume of a hydrochloric acid was equal to 25 centimeter cubed. You divide it by 1000, that will give you an answer of 0.025 decimeter cubed. So we know that of hydrochloric acid. What else do we know? The learner adds that amount of carbonate in a flask to this. And that will give us a concentration of 0.3. So we can use this. This concentration is of our hydrochloric acid. So therefore we know C of our HCl is equal to 0.3. And they want to know the initial amount of moles. So that means we are going to now take this. So we're going to write it as M of our HCl is going to be equal to our C times V. We write down the values we have on the right-hand side of the screen, 0.3 multiplied by our volume, which is 0.025. Type that in your calculator and you get an answer of 0.01 moles. Okay. And that was your initial amount of moles of hydrochloric acid that we had. Right? So, now, 7.3.2. Calculate the amount of hydrochloric acid that reacted with the unknown carbonate. Okay, so this is the part now where we're going to see, okay, this is worth 4 marks. 4 marks, yes, yeah, 4 marks. Right? So what we're going to do here is we are now going to show that we know the initial amount that we had, and now we're going to see what was also given to us. We were given this of our sodium hydroxide. 0.1 is our concentration of our NaOH. Come on, NaOH. Ah, that looks very weird. Let's erase that. So that is concentration. Yeah, concentration of our NaOH is equal to 0.1. And then we also had the volume. They said it was 15. So the volume is equal to 15 divided by 1000 is going to give you a value of 0.015 decimeter cubed of your NaOH. So now what we're going to do is we are going to now see, in this case, we are going to see what was the sodium hydroxide that were added to this hydrochloric acid. And then from that, we're going to relate it back to the ones that we calculated already. So let me show you. For our, this one out the way. So, okay. For our number of moles of our NaOH that we added now, we have the concentration and volume, so that's C times V. That is going to be equal to your 0.1, which is on there, multiplied by our 0.015. We type all of that in our calculator, and you'll get an answer of 0.0015 moles. Do not forget your units. Now, this is the amount of moles that was added of your NaOH. And now we're going to look at this over here. So we want to now see, okay, what is left? So here they say once the mixture has stopped fizzing, then this NaOH was added to neutralize any of the remaining hydrochloric acid. So that then means this is now going to be a 1-to-1 ratio because it went like that, right? So we are going to use this as a 1-to-1 ratio. So we're now going to say for our NaOH, that in terms of your number of moles for your hydrochloric acid solution was left. It's a 1-to-1 ratio in order to cancel it out. So therefore, our value was 0.0015 moles. So therefore, we can now say that the number of moles of your hydrochloric acid solution that is left is also equal to, I forgot already, 0.0015 moles. Right. Now, that is what is left that this actually was reacted to. So what you can now say is that the number of moles of your hydrochloric acid that actually reacted in this reaction. Because remember over here, where is this now? In 7.3.1, this is our initial amount that we had, right? Of the initial mole, or that 1 mole. The initial mole that we had, this was left over because this is what the NaOH was added to once the reaction completed. So what we could say is, what actually reacted in here was your number of moles of your HCl is going to be, listeners not get confused, so we write it as the initial that we had, minus the number of moles of your HCl that was left over. That is now going to be equal to your answer in 7.3.1 was 0.01 minus the answer that we just calculated in the previous one, and you can also see on the screen right now, just above here, 0.0015. And that will give you an answer of 0.0085 moles. And that is how much of our HCl reacted. And if you look over here, that is what they said. Calculate the amount of HCl, which is hydrochloric acid, that reacted with the unknown carbonate. And that was worth your 4 marks. So it's these. Now, 7.3.3. Identify element Y. And we need to show all calculations. This is going to be worth 5 marks. If you maybe perhaps have done this question, you're more than welcome to show it on your type in the chat. But this is how we're going to deal about it, right? So all of the values, or at least all of the numbers and things that we have spoken about in the previous slides is there. The only thing that is different is the question, which is 7.3.3. We now need to identify this. So the first thing that we can do now is we can now relate using the number of moles, using our mole ratio. Yeah, sorry, not number of moles, I mean mole ratio. Using the mole ratios, we can relate it to this compound because they want to deal with compounds of Y. So the first thing that we can see is we dealt with our hydrochloric acid this entire time. So we can now say that with these two, this is a 1:2 ratio. So we can now say that we will have to divide this by each other. So you can write it as a number of moles of our Y2CO3 is going to be equal to, well, is in relation to your number of moles of your HCl. I said that our HCl was 2, and this is 1. So to get that, we're going to take this value which is calculated, which was 0.0085. So now we say that 0.0085 divided by 2 because of small ratio, and that's going to give us an answer of 0.00425 moles. And this is going to be your number of moles of this. It's equal to that. Righto. Now that we have a number of moles of this element, values of this compound, we can say, using the formula, number of moles is equal to your mass divided by your molar mass. Now, were we given any of these? The answer is yes. We were given the mass over here. As you can see, it's in grams. So we have the mass and we have the number of moles. So therefore, we can then try and calculate what the molar mass is. So we'll make the molar mass the subject of the formula. So M is equal to, and that will then be now your mass divided by your number of moles. So your mass was 0.5865 divided by 0.00425. Let's just make this as a 0. So some people might think it's a 6 later on. And that is now going to be equal to 136. Because we're dealing with molar mass, this value is grams per mole. Sorry, this units is grams per mole. Now, okay, what else do we know? In this equation, other than Y2, we know we have CO3 over here. So now we need to look at that CO3 and we're going to calculate the molar mass only of that. Then we can minus the sum of that molar mass of our CO3 from this 136 to find out what the molar mass of Y is on its own. Then finding out the molar mass of Y on its own, we go look at the periodic table and then we can see what our final value is. If that was a bit too much to understand, rewatch the video and then just listen to it over and over. But I'm sure I spoke properly. So now we go with the molar mass of our CO3 only is equal to C is a carbon, so that's 1 carbon. The molar mass of carbon, you can check on the periodic table, is 12. Added to our oxygen, 3. The molar mass of oxygen is 16. Right? You're going to add this up, and that will give you a value of 60 grams per, come on, grams per mole. Where's this one? There you go, grams per mole. So, okay, now we have this. So now what we can say is that what was left over? Now in our reaction, wow, there's a lot here. So just look, okay. Let's take this, erase, here. Now I want you to focus on this part. So we dealt with this part, so we only have Y2 left over. So therefore, we can now say that the molar mass of your Y2 is equal to your 136, as you can see it's on top of the slide, minus the molar mass of your carbonate, which is CO3 on its own, which is 60. You minus that from each other and you'll get a value of 78 grams per mole. Now, don't think you are done yet, because Do you see that this is the molar mass of Y2? So now we're going to take this 78. So the molar mass of Y on its own is equal to, that's not my, please, that's the molar mass of Y, is equal to, what did I say now before that? 78. 78 divided by the 2 that we had, you type that into your calculator, and you'll get an answer of 39 grams per mole. Now you take this answer, and we go look at the periodic table. Right now, I want to show you this. So I'm going to stop sharing. Stop sharing. Okay, now I'm going to share my periodic table quickly with you so everyone can see. It'd be this. So everyone can see it right now. It's all good. If we go look now, remember our value was 39 grams per mole. Now we have to look at the number at the bottom because as you can see here, these are our molar mass here. Click on right. Okay. Anyways, so we're going to look at all of it, and what you will see is not letting me highlight, but if everyone now go look on the left-hand side, hydrogen, under it is lithium, under it is sodium, which is Na, under that is K, potassium. Look at the number under the K, 39. That is our molar mass. So if we now go back, and we go share once again, so now everyone should be able to see this once again. And here you see where it is 39. So therefore, our answer is actually going to be potassium. Right, so I just need to have this just open on the side as well, so just in case you guys have any questions. So let's write further. There. So therefore, we say that Y is potassium. If you want, you could also write that's K, a symbol. And there we go. That was our 7.3.3. I really like this question because you see, you have to literally use your stoichiometry and your periodic table, not just to get answers from it, as in like take its values. You need to eventually get a value and then look back at the periodic table. It was a very nice usage of the periodic table, which I think they should do more of. You never know, maybe they might give you a question like this in Monday's exam coming. Okay then. Now that was 7.3.3. Moving on to our last two questions, like full questions. So these are electrochemistry. Now, 8.1, a galvanic cell is constructed as shown in the diagram below. It's given over here. 8.1.1, which electrode is the cathode? Right only, nickel, or cadmium? So here we have our nickel and cadmium, but also always look at what your, so this over here. As ions is Ni plus, and this is Cd plus 2. Right, so both of it is plus 2, and remember that could be interchange. You should also say 2 plus and 2 plus. So this is how it's going to be. You go and you look at, so it's cadmium, which is Cd 2 plus, and nickel, which is 2 plus. So now, because I was speaking about the electrode, remember, before we answer it, I want you to know this. Always remember red cat. Red cat, that means reduction takes place at the cathode. So know that reduction takes place at the cathode, and if you remember, the opposites would be an ox. So oxidation will take place at the anode. Now we know also the other thing is, I know I'm giving a short lesson here, but sorry, oil rig. I need to make sure everyone understands this. Oil rig. So oxidation is when you have a loss of electrons. So whenever you find in your equation your electrons on the right-hand side of the arrow, that is your oxidation arrow. Sorry, your oxidation half reaction, because you are losing your reactants. So you are losing your electrons. That is oil rig. So please, this is a very important note for you to remember. Whenever you see the Electrons on the right-hand side of the arrow, that's the oxidation off reaction. Red cat means reduction takes place at the cathode, and ox means oxidation takes place at the anode. Oh, I don't know if a teacher taught that, but that's just the best way that I like breaking all of these up. Now, they are asking us, at which electrode is the cathode? Is it the nickel or the cadmium? So now we're going to go back and we are going to go look at our nickel and our cadmium. So by now you all probably know exactly where I'm going to be going to. Okay, so now I'm going to go to my periodic table so everyone can see as well. There we go. And just check. Can everyone see? Can you give a thumbs up? Okay, cool. Thank you. Thank you. Okay, sorry about this. This moving between screens and things can be a bit quite crazy. But thank you for that. Okay, now we're looking at this one. So we see this cadmium, which was CD, and remember it was 2 plus. So where do you find that? Well, it's over here. Here's our CD 2 plus. So it's this one over here. As you can see right now, okay, this is table 4A. Okay, it's going to be working different to how we dealt with earlier at the bottom. Let's just erase. You're more than welcome to use anyone that you are used to. But let me just explain the difference. I'm sorry that I'm doing a bit of a lesson as well, but I want you guys to pass. So, for instance, if you're using table 4B, remember table 4A is just the opposite, where lithium is at the bottom and fluorine is on top instead. So, when it comes to this, just know that if I personally like using table 4B, but if it comes like this, you first find where your metal is on the right-hand side. So you start on top. So let's say, for instance, just as an example is this, you find that first, then you basically move down on the right-hand side. When you find your element, you then write this half fraction, right? So you can go down, then from right to left, then you work your way down. Let's say, as an example, this is now where your next part is. You then write that from left to right. So for table 4B, it is in this direction, like I just showed you. In table 4A, it will be in the other direction, where you will find it from the bottom up. So you'll go from the side, up, right, up, left. I hope that made sense. Okay, now back to the lesson. CD was, bringing this over here. Yeah, CD is here. And then our nickel was Ni 2 plus. So always make sure you go choose the correct one. So here's our Ni 2 plus. Now remember, we said they want to know at which electrode does this take place at. Now remember, it's a cathode, so it's red cat, so reduction takes place at the cathode. All right? So in which of these cases is a reduction going to be taking place? Well, we moved down, we found this first, and then we write from right to left. If we're going to write that from right to left, it will be CD, and the arrow will be CD2 plus 2 electrons, and then we move down. Now remember, this is also called the standard reduction potentials, which also means when you move from left to right, that's the reduction formula. So that means our nickel is the bottom part. So our nickel is where reduction is taking place. So therefore, back to slide. Hopefully this will swap works now again. Nickel, right? And that's what everyone should see. Nickel, that's correct. So, okay. So that's how we get this answer. I see someone, okay, I have a question. So let me try and get that quickly. So yes, remember, if you have a question, please write it in the chat because we did not enable your mic. I use table 4B. So in that case, I use table 4B, please. So everyone just take note of that. Okay, so like I said, you're more than welcome to use any table that you are used to, but this is the one that I just used. So I'll swap these two around and I can see what you guys are saying. Okay, but so far, does everyone understand what's happening? You can give thumbs up. Okay, good. Okay, so we're at the end of the list. I'm so sorry, guys. Okay, yes, there we go. Sheetless. Okay, so this is how it goes. So it's nickel. Yeah, all of that just for one mark, just to show you nickel. But I am sure you guys understand now. Table 4B, and I know I gave you a short lesson. I'm not sure if everyone knew that, red cat and all of those things I said, but that's how you use it. Moving on to 8.1.2. Write down the equation of the oxidation half reaction of the cell. So in that case, if our reduction was our nickel reaction, then that means our cadmium is the oxidation half reaction. And remember, I said whenever you have a oxidation reaction, your electrons is on the left-hand side. So that means we'll have it like this. Okay. Here we go. I think I'm going to do it this way instead, so I don't have to stop sharing every time. So therefore, if I take this off, it is there. So that means our cadmium would now be, when we write from our, where we have our electrons on the right-hand side of our arrow. So you're going to write it like this. We worked our way down. We found cadmium. So you write down cadmium first. And then even though I'm saying you're now going to write down from right to left, when you write it in your formula, as you can see right now, a CD2 plus 2 electrons, it should look like this. There we go. So see, still CD is equal to that. So that is our half reaction for our oxidation half. Moving on. 8.1.3. How will the reading on the voltmeter be affected if the concentration of the nickel ions is increased after the cell reached equilibrium? Right? So how did this actually increase after the cell reached equilibrium? Here we need to choose from increase, decrease, or remain the same, and give a reason for your answer. So here we see, okay, the galvanic cell, that is the diagram that was given, and this is all that was given over here, right? So now we need to increase, decrease, or remain the same. Now remember, the way this works is you will have a substance that will always give away its electrons, and the other substance will accept those electrons. So out of these, our cadmium is the part that was giving away its electrons, and our nickel was the part that was accepting our electrons, right? Where reduction was occurring. So if that's the case, we can say that the increase in our nickel will now favor our forward reaction, and then therefore we can actually say that the overall part would be increase, right? Because this is now process gaining our electrons more, right? So we increase it like this instead. Now, moving on, 8.2. Consider the following standard electrochemical cell, as given over here. Initially, each half cell contains 200 centimeter cubed of our electrolyte. So there we can see we have centimeter cubed. We might have to change to decimeter cubed. Remember, always divide by 1,000. The cell is connected to a circuit and allowed to produce current until the concentration of the electrolyte in the cathode half cell is reduced to 0.5 moles per decimeter cubed. There we see we have decimeter cubed already. So that means we will need to convert our initial amount also into decimeter cubed. Then as stated, let's click. The cell is then disconnected. Write a balance equation for the net ionic cell reaction. So in this case, as now not just speaking about our cadmium and our nickel that we had, this is 8.2, so it's a completely different section that we have. Here you can see that we were given our copper, and this is in its, because it's a galvanic cell, and we know that was giving scientific notation. Whenever it comes to that, the way I like remembering it is, remember our alphabet starts with A. So when you deal with let's get this marker. When you deal with your cell notation, alphabet starts with A. So we start this part off with the A. So that's where our anode is, which means this is where our cathode is. Right? Difficult to write with the mouse, but that is our anode electrode, and then this should be our anode electrolyte. All right, so that will be our anode electrode. So that will be our anode solution or electrolyte. And this will be our cathode solution, and that will be our cathode on its own. Yes. So now we need to write down the balance equation. So we have our Cu and Cu2 plus and Ag1 plus and Ag. So we're going to look at our table 4b. Erase our Cu2 plus, which is this one over here. Cu2 plus, this one over here. But no, sorry, because you see this one is giving us a Cu plus, so it's wrong. We're going to look, there's quite a few of Cus on here, so we're going to get that. Yeah, it's this one. This one gives us a value with Cu on its own. The other one was our Ag plus. Here is it. We make sure always using correct table. This was correct table 4b. Remember, you could use either one. When I say correct table, I just mean the one that you are used to using. Don't swap between the two. So that means we go down, we found this, and then we go from right to left. This is going to be where oxidation takes place. So because oxidation takes place here, you know that is your anode, as we see now in our cell notation, and then this is where reduction took place. So here you see that we have 2 electrons. That's over here, right? 2 electrons, and here is only 1 electron. They wanted a balanced formula. Come over. There we go. So here they want a net balance equation that we have. So we now need to, of course, make this balanced. So you're going to multiply these in by 2, and then this will be your balance equation, where you get rid of your electrons, and then you have your values as Cu, and then 2Ag plus will give you 2Ag solid, and then your copper. 8.2.2. Calculate the concentration of the electrolyte in the anode half cell when the cell is disconnected. So, okay, now this is going to be a very, very long answering question, because here you will see that it is worth 7 marks. So here you'll see we have it as in each half reaction it was 200. So that means we have a volume of 0. That would be 0.2, because you divide it by 1000. So that is 0.2. What else were we given? The cell is connected, the cathode off, and that was this. All right, the cathode off, which was the cathode off is this, your silver. Right, that should be your silver, which is your cathode off, because the side is your anode. Now, what we're going to do is we are going to break this up into its different sections. I am now going to first calculate our cathode. So let's write cathode, so we all know where I am. In the cathode section. The cathode, if we looked at our table 4b, we said that now this is now going to be our 2Ag plus 2Ag plus 2 electrons will eventually give us 2Ag. Right? And that's going to be our cathode reaction. Now, what we can do here is we can now go and write down, move this out of the way. We can write down the number of moles of this. So number of moles of our Ag plus, and this is the amount that was reacted, going to be equal to the concentration that was given. So that is C times V. So that is going to be our 0.5 multiplied by the volume that we just got, which was 0.2. 0.2. You type that in your calculator and you get an answer of 0.1 moles. Right. This is the part of our cathode that actually reacted. Now, we want to link that up with our copper. So this we need to link up with our copper. And you can see in our reaction, this is how it was. In our reactant side, we dealt with this, and now we link it up to our copper. What's the mole ratios? 2:1. Right? Remember, that's a 1 over there. So we're going to write that down now. So our number of moles of our copper, so our Cu that actually reacted, in terms of brackets, in terms of the number of moles of our silver ion that reacted is equal to 1:2. So therefore, you're just going to say the number of copper that reacted is equal to. You're going to say that is your, let's look up. That should be this one here, yes. The 0.1. So we bring that. That's going to be our 0.1 divided by 2. And that will give an answer of 0.05 moles. Oh, that's a different M. And that is 0.5 moles. 0.05 moles. Sorry. Yes. Now, all of this is when we dealt with our cathode. And that's how we related it to our copper that actually reacted. Now we'll move on. And now we're going to find out what happened by the anode. So we'll write that as anode. So it's the same system. So anode, what was the formula there? In this case, it was our Cu. You can look at your table 4b, but you'll see that that is Cu, and that will give you Cu2 plus, which are electrons, and that goes to your two electrons. Let's take it away just in case people might think later, what was that small part over there? So that is the spot. Now we're going to link those two that we just calculated together, because we just calculated the number of moles of our Cu, which was this 0.05. Now we relate those together. We go to our balance equation, so I do not lose anyone. Here is our Cu2 plus 1:1 ratio. Let me put the arrows together so you can follow along. 1:1 ratio. So we'll write that down. The number of moles of our Cu that reacted, and this is compared to our number of moles of our copper ion, so Cu2 plus. That was actually released. That was given off, right? That is a 1:1 ratio. So therefore, we now can say a number of copper ions that was released is also equal to, if we go back, 0.05. So that is 0.05. Is everyone still following along with me? You can just give a thumbs up. Okay, perfect. Good, good. I'm just making sure that, okay, you guys are still following along. Good, 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 good. Now that we have what this is being dealt with, we're not done, because now we need to find out if this was the amount of copper that was released, what did we begin with? So this 0.05, we are now going to relate this to this part over here. You'll see here we have our volume of our 0.5. As you can see, this volume over here, our 0.5. All right, so we had that, and its initial amount was going to be 1, right? Because we began with a 1, and then we eventually had a 0.05 that was released. So we are going to now say that our number of copper, because it was a 1:1 ratio, number of our copper, which is Cu2 plus, initially, this is what we want to try and calculate. That's going to be our concentration multiplied by our volume. Now the concentration is going to be 1 multiplied by our 0.2, and that's going to be equal to 0.2. Now you're going to say the number of moles of your Cu2 plus final is going to be equal to the number of moles of your Cu2 plus, let's put all of that in brackets, initial added to the number of your CU. There's a way to have a bracket and a C, but okay. As long as you guys see what I'm doing. So number that, so it is Cu2 plus, it is released. Now we're going to take these values. This 0.2 as well as this 0.5 that was released. So now we're going to take that and we're going to add the two together. So that is going to be our 0.2 added to our 0.05. And that will give us a value of 0.25 moles. Now, all of that is eventually showing us what our number of moles of our copper ions was released. But guess what? That 7 marks, we won't get all of it by this time. Because if we move all the way back, they say calculate the concentration of the electrolyte on the half cell. So because we need to calculate the concentration that was done over here, we're going to use this number of moles. And we're going to deal with the volume that was given was 0.2. So here you can say the concentration of your, come on, copper Cu2 plus is equal to your number of moles, which we just calculated, divided by your volume. So that's going to be equal to, the answer that was on the previous slide was 0.25. If you do not believe me, there it is. Let's make that a 5 so you can see it clearly. Divided by 0.2, and that was given at the beginning. All of that is going to be equal to 1.25. This is concentration, so that is moles per decimeter cubed. And that is where you're going to get your 7 marks. Yes, quite a long one. But that was our 8.2.2. So, okay, now moving on to question 9, our last question, and then you guys are free to go study again. So, question 9 was a bit of a, how do I say, not a tricky one, but there was a bit of miss things written down. So I don't know if you have tried this question out yet. If you have, you might have seen it as well. For 9.2 is where there was something that you should not actually answer that because it is wrong, as well as 9.3.1. But I'll show you now as we move on. Now, question 9. Electrolysis is generally used in industry to produce chemicals through the decomposition of compounds. The simplified diagram below represents an electrolytic cell used in the electrolysis of a concentrated sodium chloride solution. Sorry, I just need to admit some people into the meeting. Okay. Okay. Moving on. 9.1. Define the term anode in terms of oxidation or reduction. So by now you're probably remembering already, read cat and anox. So define the term anode in terms of oxidation or reduction. Remember it's anox, so we know oxidation takes place at the anode. So therefore this answer is, the anode is the electrode where oxidation takes place. So see, I'm not just making up these shorter languages or things, whatever you call that. It's true. 9.2. Which electrode, X or Y, is connected to the positive terminal of the power source? Give a reason for your answer. Now, they did not give us enough. They did not give us enough information to see what is a positive and negative section over here. So 9.2 is not going to be answered. So even though it was worth 2 marks, it was said that we should it should not be marked. Right? So 9.2, skip that. 9.3.1. Write down the name or chemical formula of, and yeah, they should say gas A. So this is going to be gas A. Okay, I moved a bit too fast in my presentation, but there I think you guys mostly already saw it. It's going to be a chlorine gas. All right, so your chemical formula over here is going to be the one on the left-hand side. They meant it of gas A. The marker, here we go. This is gas A. So what was given? Concentrated sodium chloride. So what is the gas between these two? I'm not going to use that as sodium. I'm not going to use sodium gas. It's chlorine gas, right? So it is Cl. The chlorine is your gas at here. Then the part that's not going to be marked again was this 9.3.2, compound C, because they did not tell us too much information of this solution E over here. You see, this was like unknown, and here was unknown. Eventually, what's supposed to be was water. That was not known, so this was also a skipped question. 9.4. Write down the equation for the half reaction that takes place at the cathode of the cell. And this is going to be worth 2 marks. So because we have all of these over here, they said electrolysis is generally used in order to produce the decomposition of these compounds. So a lot of this is what they supposed to have given, but because they didn't, on the right-hand side, the gas is supposed to be water, and this is what your formula is supposed to be. Then it came to 9.5. We have to refer to the relative strengths of oxidizing agents to explain this answer. In general, if you go look at the table 4b, you will find that water is a stronger oxidizing agent than sodium, and that will then be reduced. Another thing is, I also just want to say, because this was the last part of the question, I know most people's like, I mustn't teach while I do this, but I'm trying to just throw a few things you need to know out. Please never ever get confused between oxidizing agent and a reducing agent. If they say you have a reducing agent, oxidation occurs. If you have an oxidizing agent, reduction occurs. Reduction. A way that I like remembering it is, I don't know if you guys like watching movies, but when it comes to movies, I don't know if you like watching the spy movies, but you have those things such as like double agents, where they're working for the one team, but they're actually working for the other team. So I remember this is, whenever I see the word agent, the word that comes before it is opposite to the process that happens at it. So a reducing agent is where oxidation occurs. Oxidizing agent is where reduction occurs. And maybe that might help you in exams. But that's just my 2 cents I'm throwing out over there. Other than that, I really hope that this lesson was beneficial for you and helpful. Also, I'd like to say a very big thank you for joining us for this lesson. And I hope it's going to help you for your test on Monday. All the best for the rest of your exams. And I hope that you are going to ace the test. So on behalf of myself, as well as everyone on Astron Energy, I'm going to, we will thank you. And yes, I'm just checking the chats here. I see somebody saying about the recordings. I'm going to try and get it uploaded by today so that you can, so before I go home now, I'm going to try and upload it. And then hopefully by today, so let's say maybe 2 o'clock, 3 o'clock for the latest, you'll have this lesson that you can go through. Remember, it's on the YouTube link. You just focus on that as well. Same as the other lessons. If you're not sure, it's on the Cape Town Science Center's YouTube channel, and you go check over there. It's under exam preparation, that playlist. Dealing with grade 12. But really, I hope you all enjoyed this lesson. I hope I made it nice and interesting for you, and I hope you have learned at least a few things from today's lesson. But thank you again, and all the best for your exams. Goodbye, all.